Hello there, and welcome to Nightfall Science. Tonight, we explore a haunting possibility that long before humans, another intelligent civilization may have risen, changed the planet, and disappeared so completely that Earth itself erased nearly every trace. Let's begin. To imagine a civilization before humanity, we must first loosen our sense of time. Human history feels ancient when measured in generations. A century can seem distant. 1,000 years can feel almost unreachable. Civilizations such as ancient Egypt, Mesopotamia, the Indus Valley, and the Maya appear to belong to worlds separated from us by enormous stretches of time. Yet, from Earth's perspective, all recorded human history occupies only the thinnest layer. Our planet formed around 4.5 billion years ago. If the entire history of Earth were compressed into a single 24-hour day, modern humans would appear only during the final seconds before midnight. Cities, writing, machines, and industry would arrive almost at the very end of the final second. Everything humanity has built would be little more than a brief flicker across the surface of an ancient world. Before us, Earth passed through ages almost too long to imagine. Continents assembled and broke apart. Mountains rose from the ocean floor and slowly dissolved beneath rain. Seas opened where deserts once existed. Forests spread across enormous regions, only to vanish as climates changed. Entire branches of life appeared, flourished, and disappeared. For hundreds of millions of years, animals walked beneath skies that no human eye would have recognized. And through all of this, Earth continued reshaping itself. The ground beneath us may appear permanent, but it is not. Rock is broken by wind, water, ice, heat, and chemical reactions. Rivers carry pieces of continents toward the sea. Ocean floors sink slowly into the planet. Volcanoes create new land while erosion removes old landscapes. Earth does not preserve its history like a carefully protected library. It edits, it recycles, it buries one chapter beneath another. This is why the possibility of a forgotten civilization becomes so difficult to examine. A civilization might build roads, towers, factories, ports, mines, and machines. To those living within it, these structures could appear strong enough to survive forever. But forever is not the same for a city and a planet. Leave a modern city abandoned for a few decades, and vegetation begins pushing through cracks in the pavement. Water enters buildings, metal rusts, wood decays, roofs collapse, tree roots widen fractures in concrete, animals make homes inside empty rooms. After centuries, many structures would become ruins. After thousands of years, most exposed buildings would disappear almost completely. Stone foundations might remain. Tunnels might survive underground. Ceramics and glass could endure in scattered fragments. Yet even these objects would face burial, erosion, pressure, and chemical change. After millions of years, the landscape itself could be gone. The river beside the city might change course. A coastline could move hundreds of kilometers. Glaciers might scrape across the region. Sediment could bury everything beneath thick layers of rock. Tectonic forces might lift the land into mountains or pull it downward beneath an ocean. And if enough time passed, the plate carrying those remains could sink into Earth's mantle, where heat and pressure would erase nearly every recognizable trace. Humanity has existed for only a tiny portion of geological time. Our industrial civilization is younger still. The first factories, railways, electrical systems, automobiles, and large-scale chemical industries appeared only recently. From the viewpoint of geology, the entire industrial era is almost instantaneous. This leads to a strange question. Suppose an industrial civilization had appeared millions of years before humans. Suppose it lasted for 10,000 years. That would be an extraordinary duration compared with our own industrial history. Its inhabitants might have explored their world, transformed landscapes, extracted resources, altered the atmosphere, and filled their planet with technology. Yet against a background of millions of years, their entire existence would form a very narrow geological signal. 10,000 years sounds enormous to us. To Earth, it is a brief event. A civilization could rise and disappear between two thin layers of sediment. Its history might be compressed into a band of rock no thicker than a human hand. This idea lies near the heart of what scientists sometimes call the Silurian Hypothesis. The name is slightly playful. It does not suggest that scientists have discovered an ancient civilization from the Silurian period. The Silurian was a geological interval more than 400 million years ago, long before dinosaurs and long before complex life became common on land. The title was inspired partly by science fiction, where intelligent reptilian beings are sometimes imagined as Earth's earlier inhabitants. The real scientific question is more careful. If an industrial civilization had existed on Earth millions of years before humans, would we be able to detect it today? This is not the same as claiming that such a civilization truly existed. There are no confirmed ancient machines, artificial cities, or technological artifacts from a pre-human species. No accepted fossil record reveals an older industrial society. Instead, the hypothesis is a thought experiment. It asks scientists to examine how civilizations affect planets and how long those effects remain visible. The question is useful even if humanity is the first technological species on Earth. By considering what traces an older civilization might leave, we can better understand what our own civilization is placing into the geological record. We can also improve the search for technological life on distant worlds. Perhaps alien civilizations would not be discovered through spaceships or radio messages. Perhaps their presence would be revealed through changes in a planet's atmosphere, climate, chemistry, or sediment. The mystery, therefore, begins not with ruins, but with evidence. What evidence does a civilization leave behind? Our minds naturally imagine familiar objects: a metal tool, a carved monument, a buried building, a road disappearing beneath a forest. These are archaeological remains, and on human timescales they can be powerful. Archaeologists reconstruct entire cultures from pottery, bones, foundations, seeds, inscriptions, and fragments of tools. But archaeology normally reaches across thousands or tens of thousands of years. The Silurian question reaches across millions. At those depths of time, individual objects become much less reliable. Fossilization itself is rare. Most living organisms never become fossils. When an animal dies, it is usually eaten, scattered, dissolved, or decomposed. Its bones may be broken. Its body may rest in a place where sediment never protects it. For fossilization to occur, conditions must be unusually favorable. The remains often need to be buried quickly. Minerals may slowly replace biological material. The surrounding rock must then survive erosion, heat, pressure, and tectonic recycling. Finally, the fossil must become exposed in a place where someone can discover it. Every fossil is the survivor of a long sequence of unlikely events. Entire species can live for millions of years while leaving behind only a small number of known fossils. Some may leave none that we have found. Even the fossil record of large and successful animals remains incomplete. Dinosaurs dominated terrestrial ecosystems for more than 160 million years. They lived across every continent. They produced unimaginable numbers of individuals. Yet only a small fraction of those animals became fossils, and only a fraction of those fossils have been discovered. A technological civilization could be numerous and widespread, but if it existed briefly, its bodies alone might be surprisingly difficult to identify after deep time. Cities would create concentrated areas of unusual material, but cities occupy only a tiny portion of a planet's surface. Modern urban regions feel enormous because people live within them. Seen from orbit, however, they cover relatively small areas. Compared with oceans, deserts, forests, and ice sheets, cities are narrow islands of construction. A future geologist searching randomly through ancient rocks might easily miss them. The ocean creates an even greater challenge. Most of Earth's surface lies beneath water. Oceanic crust is constantly formed along volcanic ridges and destroyed where tectonic plates sink into the mantle. Very little ocean floor is truly ancient. Much of it is younger than 200 million years. Any coastal civilization built hundreds of millions of years ago might now lie within crust that no longer exists. Ports, ships, roads, and settlements could have vanished with the plate beneath them. Continental rocks can survive longer, but they are also disturbed. They fold, they fracture, they melt, they are buried beneath sediment or stripped away by erosion. The oldest exposed rocks on Earth are rare fragments from the planet's distant youth. Most ancient landscapes are no longer preserved in their original form. This means the absence of obvious ruins does not immediately answer the question. If no ancient city has been found, perhaps there never was one. That is the simplest explanation, and it remains the most reasonable conclusion based on current evidence. But scientifically, we must also ask whether such cities would be expected to survive. A missing signal can only be meaningful when we understand how easily that signal could disappear. Imagine placing a smartphone in an open field. At first, it would be unmistakably artificial. Its surface would be smooth. Its materials would be refined. Its internal circuits would contain carefully arranged metals and manufactured compounds. After years of exposure, water would enter it. Its battery would degrade. Its casing would crack. Plants might grow around it. Sediment could cover it. After thousands of years, its recognizable shape might be lost. Some metals would corrode and spread into the soil. Glass might remain as fragments. Synthetic materials could persist longer, but they too would change through heat, pressure, radiation, and chemical reactions. After millions of years, it may no longer appear as a device. Instead, it might survive only as an unusual concentration of elements, a thin chemical anomaly, a strange particle trapped inside rock, a pattern that would be easy to overlook unless someone knew what to search for. The same could be true of an entire civilization. Its strongest evidence might not be a buried machine. It might be a disturbance in the carbon cycle, a sudden change in global temperature, an unusual layer of metals, a brief increase in erosion, the chemical remains of artificial materials, a pattern of extinction, a shift in the balance of isotopes preserved within ancient sediments. In other words, the most enduring monument of a civilization may be the planet it changed. Human industry is already leaving signals of this kind. We burn carbon that remained buried underground for millions of years. We move enormous amounts of rock and soil. We produce plastics, concrete, aluminium, radioactive materials, fertilizers, and synthetic chemicals. We alter rivers, coastlines, forests, and the chemistry of the atmosphere. Future geologists may not find our cities intact, but they could detect a sudden boundary within the rocks. They might see a rapid change in carbon isotopes caused by fossil fuel burning. They might find microscopic plastic particles buried in marine sediments. They could discover unusual concentrations of industrial metals. They may notice the spread of domesticated species across continents. They could identify a sudden decline in wild biodiversity. Our civilization is writing a chemical signature. The writing may become faint, but parts of it could remain long after our buildings disappear. This raises a quiet and unsettling possibility. Could similar signatures already exist in ancient rocks? Earth's history contains many abrupt changes. There have been episodes of rapid warming, sudden shifts in carbon chemistry, ocean acidification, mass extinctions, periods when oxygen levels changed, moments when enormous volcanic eruptions transformed the atmosphere. At first glance, some of these events may resemble the effects of industry, but resemblance is not proof. Nature can produce dramatic planetary change without intelligence. Volcanoes release greenhouse gases and metals. Asteroid impacts spread dust, melt rock, and ignite fires. Changes in ocean circulation affect climate. New forms of life can transform the atmosphere. The rise of photosynthetic organisms filled Earth's air with oxygen, producing one of the greatest environmental revolutions in planetary history. No machines were required. To identify an ancient civilization, scientists would need evidence that could not be explained more convincingly by natural processes. That is extremely difficult. An unusual carbon signal might come from industry, but it could also come from volcanic activity or the release of methane. A metal-rich layer might suggest mining, but it could result from changing ocean chemistry. A sudden warming event might resemble our present climate, yet arise through natural feedback systems. Science must prefer explanations supported by the greatest amount of evidence. Extraordinary possibilities require more than a mysterious pattern. They require a collection of signals that fit together. Perhaps artificial molecules would appear alongside unusual isotope ratios. Perhaps geological layers would contain materials formed only through controlled manufacturing. Perhaps there would be evidence of rapid resource extraction, widespread combustion, and synthetic compounds within the same narrow interval. Even then, researchers would move carefully. Deep time changes materials. Chemical signatures become blurred. Sediments are mixed by organisms. Heat alters molecules. Pressure transforms minerals. A clear signal can fade into ambiguity. The search is therefore not like discovering a hidden temple. It is more like listening for a quiet note inside a storm that ended millions of years ago. And before we search those ancient layers, we must ask another question. Could intelligence have evolved before humanity? Earth has produced many remarkable forms of cognition. Crows solve complex problems. Octopuses explore, learn and manipulate objects. Elephants remember landscapes and appear to mourn their dead. Dolphins communicate, cooperate, and recognize themselves. Other primates create tools, form alliances, and pass behaviors between generations. Intelligence is not limited to one branch of life. Yet human technology required more than intelligence alone. It depended on hands capable of precise manipulation, social learning, language, long childhoods, access to fire, stable environments, accumulated knowledge, and perhaps many accidents of evolution. A highly intelligent animal living in the ocean might never develop metallurgy because fire cannot be maintained underwater. A species with limited ability to manipulate objects might understand its environment without building machines. Another species could develop complex culture but leave few physical traces. Civilization is not an inevitable destination. Evolution does not move toward technology with a predetermined plan. It responds to local pressures. A species only needs to survive and reproduce within its environment. For millions of years, dinosaurs succeeded without cities. Sharks survived repeated mass extinctions without industry. Bacteria transformed the entire planet while remaining microscopic. Humans are not evolution's final goal. We are one unusual outcome among countless possibilities. Still, the age of Earth leaves room for imagination. Complex animals have existed for more than 500 million years. Humans have used industrial technology for only a few centuries. The window between those two facts is immense. Could another species have approached technology during that time? Current fossil evidence gives us no reason to believe that one did. But the Silurian Hypothesis invites us to examine the limits of what the fossil record can reveal. It reminds us that geology preserves events unevenly. Some moments survive in extraordinary detail. Others vanish almost completely. A footprint may harden into stone and remain for hundreds of millions of years. An entire forest may disappear without leaving a recognizable tree. A volcanic eruption may create a global chemical marker. A city might become nothing more than scattered particles. The deeper we travel into Earth's past, the less the planet resembles a museum. It becomes a damaged manuscript. Most pages are missing. Others have been overwritten. Some remain only as fragments pressed between layers of stone. And somewhere within those fragments, Earth carries the history of every world that ever existed upon its surface. Ancient oceans, lost continents, strange forests, unfamiliar animals, perhaps nothing more, perhaps something we have not learned to recognize. For now, the ground remains silent. No ancient highway emerges from a cliff. No machine rests within coal older than the dinosaurs. No confirmed artificial structure waits beneath the sea. The evidence supports a planet where technological civilization appeared only recently, through humanity. But the question is not closed, simply because the answer appears unlikely. Instead, it becomes more precise. We should not ask only whether ruins remain. We should ask what a civilization would do to a planet. We should search for chemical fingerprints, unusual materials, and sudden changes that survive when cities do not. Because after enough time, Earth may erase every name, every language, and every monument. Yet even an erased civilization might leave behind one final shadow, a thin line hidden inside the rocks, a brief disturbance in the planet's breathing, a message without words, waiting beneath our feet. Imagine that humanity disappeared tonight, not through war or disaster, not through one dramatic moment visible from space. Simply imagine that, for reasons unknown, every human being quietly vanished. The planet would continue moving. Morning would arrive. Sunlight would spread across empty streets. Traffic lights would continue changing from red to green, directing vehicles that no longer moved. Computers would remain active inside silent offices. Messages would travel through networks with no one left to read them. For a few hours, civilization might appear almost normal. Machines would hum. Ventilation systems would move air through buildings. Satellites would circle overhead. Power stations would continue supplying electricity wherever automated systems remained stable. But without human attention, the first failures would begin quickly. Electrical grids require constant balance. Power must be generated at nearly the same rate that it is consumed. Engineers monitor fluctuations, redirect energy, repair damaged equipment, and respond when storms or accidents interrupt transmission lines. Without them, different parts of the grid would begin shutting down. Some areas might remain illuminated for several hours. Others could last longer, especially where local systems continued operating automatically. But one by one, cities would go dark. At night, the glow visible from orbit would begin to fade. The great web of artificial light stretching across continents would break into scattered islands. Then those islands would disappear. Emergency generators would activate in hospitals, laboratories, communication centers, and industrial facilities. They would operate until their fuel was exhausted or a mechanical failure occurred. Within days or weeks, much of the world would lose power. Pumps would stop moving water through buildings. Heating and cooling systems would fall silent. Elevators would remain trapped between floors. Digital information stored inside active machines would become inaccessible. The disappearance of electricity would not erase civilization immediately, but it would remove the energy holding many of its systems together. Modern cities may appear solid, yet they depend upon continuous maintenance. Water must be kept outside underground tunnels. Drainage channels must remain clear. Steel must be protected from corrosion. Concrete must be repaired as it cracks. Vegetation must be removed from roads, walls, and foundations. Without these small and constant acts, the structures around us would begin returning to the environment from which their materials came. Rain would enter through damaged roofs. During winter, water inside cracks could freeze and expand. Each cycle of freezing and thawing would open those fractures slightly wider. Summer heat would expand materials. Cold nights would contract them. Wind would loosen panels and roofing. Storms would remove glass from windows. Birds would enter through the openings. Seeds carried by the wind would settle in gutters filled with dust and leaves. At first, a few grasses might appear, then small shrubs. Eventually, tree roots could push into walls and foundations. A seed requires only a narrow opening. Given enough seasons, that opening could become a wound running through an entire building. The city would not be destroyed by one powerful force. It would be dismantled gently by countless ordinary processes. Water, wind, roots, salt, heat, cold, gravity. The same natural forces that shape mountains would begin working upon towers, bridges, and roads. After several years, many wooden buildings would suffer severe decay. Fungi and insects would break down beams. Roof damage would allow more water inside. Floors would weaken. Walls would lean. Some houses might remain recognizable for decades, especially in dry regions. Others would collapse much sooner in humid forests or along stormy coastlines. Climate would decide much of what survived. A structure in a frozen desert might remain visible long after a similar structure in a tropical environment had disappeared beneath vegetation. Metal would also change. Iron and steel are useful because they are strong, abundant, and easy to shape. But refined iron is not always stable when exposed to oxygen and water. It rusts. The smooth beams of bridges would become rough. Bolts would weaken. Reinforcing bars hidden inside concrete would expand as corrosion formed around them. This expansion would break the concrete from within. Small cracks would become larger. Pieces would fall away. A bridge might remain standing for many years, appearing strong from a distance, while its internal supports slowly lost their ability to carry weight. Eventually, one section would collapse, then another. Rivers would continue moving beneath the broken structure, carrying pieces downstream and covering others with mud. Modern skylines would lose their sharp edges. Glass towers would become open frames. Steel columns would bend beneath their own weight. Upper floors might fall into lower ones, creating compact hills of concrete, twisted metal, and dust. For a time, these ruins would remain unmistakably artificial. Straight lines would cross the landscape. Walls would stand where no natural cliff should exist. Roads would cut through forests. But nature would soften those patterns. Leaves would cover the pavement. Roots would lift and split it. Soil would accumulate inside cracks. Asphalt would fragment into dark stones. In wet climates, forests could eventually hide highways beneath trees. In dry climates, sand might drift over them. In northern regions, advancing ice could scrape away entire cities. Along coastlines, waves would attack buildings from below. Sea levels naturally rise and fall over geological time. A city built near today's shore might one day lie beneath the ocean. Another might stand far inland as water retreated. Ports would be among the first urban areas to disappear. They are constructed beside energetic environments, where tides, storms, currents, and waves constantly move sediment. Piers would collapse. Ships would sink or break apart. Sea life would cover metal surfaces. Wooden structures would be eaten by organisms or buried in mud. Concrete harbors might survive for a time as unusual reefs. Fish would move through windows. Corals could grow across walls. From above, the drowned city might remain visible beneath clear water for centuries. Then sediment would settle across it. The outlines would fade. Eventually, only scattered foundations and strange concentrations of material might remain beneath the seabed. The ocean is capable of preserving objects when burial occurs rapidly. Low oxygen and fine sediment can protect organic material from some forms of decay. But the ocean can also be destructive. Salt accelerates corrosion. Currents scatter remains. Pressure increases with depth. And over millions of years, the ocean floor itself moves. New crust forms where molten material rises along underwater ridges. Older crust travels away from those ridges and may eventually descend into the mantle at deep ocean trenches. A civilization built upon oceanic crust could lose not only its structures, but the ground that once supported them. The plate itself could be consumed by the planet. Continents survive longer, but they are not motionless. They drift slowly across Earth's surface. They collide, they stretch, they rotate. A coastal plain may become a mountain range. A desert may become the bottom of a sea. A quiet region may be broken by faults or buried beneath lava. The places humanity considers permanent are only temporary arrangements of land. Even mountains are passing forms. Rain removes grains from their peaks. Rivers carry those grains into valleys and oceans. Over tens of millions of years, a mountain range can be worn down until only its deepest foundations remain. If nature can remove mountains, it can remove cities. Yet different materials would vanish at different speeds. Paper would be among the most fragile. Human civilization stores enormous amounts of knowledge in books, records, letters, photographs, and printed documents. Inside dry, protected buildings, paper can survive for centuries, but exposed to moisture, microorganisms, insects, fire, and changing temperatures, most books would decay. Libraries might remain intact for a time. Rows of silent volumes could stand in darkness while dust accumulated around them. Then water would enter. Pages would swell and stick together. Ink would spread, mold would grow, shelves would collapse. The languages, histories, and ideas recorded there would slowly become stains within rotting material. Stone inscriptions might survive longer. Carved letters can endure for thousands of years, especially when protected from erosion. But even stone is not immortal. Different minerals react with water and air. Acidic rain dissolves some surfaces. Wind carries abrasive particles. Heat and pressure can erase carved features. A message intended for eternity may become unreadable long before the rock itself disappears. Digital information is even more vulnerable than it appears. Humanity stores much of its knowledge as patterns of electrical charge or magnetism. These patterns can be copied perfectly, but they require functioning devices and systems. A hard drive is meaningful only while its internal structure remains readable. A server requires electricity, cooling, and maintenance. Cloud storage sounds distant and almost weightless, but it exists inside physical machines placed within buildings. Without power and human care, most digital archives would become silent objects. Their information might remain for a while, but corrosion, heat, moisture, radiation, and material degradation would slowly damage the stored patterns. Even if a future intelligence discovered an intact device, it would need to understand how to power it, read it, and interpret its codes. A dark piece of glass or metal might contain an entire library while appearing completely meaningless. Knowledge can survive physically and still remain lost. Ceramics might be more fortunate. Humans have used fired clay for thousands of years. When clay is heated, its structure changes. It becomes hard, stable, and resistant to ordinary decay. Pieces of pottery are among the most common objects recovered from archaeological sites because they do not rot like wood or fabric. If humanity vanished, fragments of plates, bricks, tiles, toilets, electrical insulators, and industrial ceramics might survive for extremely long periods. They would break. Their surfaces would wear away. Minerals might replace or coat them. But some fragments could remain recognizable long after most buildings disappeared. Glass could also persist. Windows would shatter early, creating fields of fragments around collapsed structures. Over time, sharp edges would become smooth. Chemical reactions would cloud the surfaces. Heat and pressure could change the material. Some glass might eventually resemble natural stone, but unusual compositions or concentrated layers could reveal that the material had been manufactured. Concrete would leave a complicated legacy. Humanity produces it on an enormous scale. It forms buildings, dams, tunnels, roads, foundations, seawalls, and bridges. Fresh concrete can appear permanent, yet it cracks, reacts with water, and breaks when steel inside it corrodes. Large structures would fragment. The pieces would become smaller through repeated weathering. Rivers might carry them away. Waves could grind them into artificial pebbles. Some fragments would enter future sedimentary rocks. There, they might become part of a new material, made from both natural stone and the remains of construction. A future geologist might discover rounded pieces of concrete mixed with plastic, glass, shell, sand, and metal. The city would no longer exist, but the stones made by the city could survive. Aluminium might create another unusual signal. It is common within Earth's crust, but naturally, it is usually bound within minerals. Producing pure aluminium requires significant energy and industrial processing. Modern civilization has created enormous quantities of it. Aircraft, cans, buildings, vehicles, cables, machines, and electronic devices all contain aluminium in refined forms. After abandonment, much of it would corrode or react with surrounding materials. Yet unusually concentrated aluminium compounds could enter sediments. The original objects might disappear, while their chemical presence remained. Copper, chromium, nickel, lead, and other metals could also create strange distributions. Mining gathers elements that were once scattered across large volumes of rock. Industry then concentrates them inside cities, machines, landfills, and waste deposits. When those objects decay, the metals do not cease to exist. They move. They dissolve into water. They attach to soil particles. They enter organisms. They settle into lakes and oceans. Millions of years later, they may survive as thin layers containing combinations rarely produced by ordinary geological processes. Landfills could become some of the richest archaeological sites of our civilization. They are often viewed as places where unwanted things disappear, but nothing truly disappears there. Household objects, food packaging, broken electronics, clothing, chemicals, glass, metal, plastic, and construction waste are compressed together and covered with soil. In the early years after abandonment, landfills would change rapidly. Organic material would decompose, gases would form, water would carry dissolved chemicals through the waste. Layers would settle and shift. Fires might burn underground. Eventually, the remaining material could become compacted beneath new sediment. Most objects would lose their original shape, yet the mixture itself would be unusual. Natural sediments normally sort materials through wind, water, gravity, and biological activity. A landfill combines them through human behavior. Rare metals might appear beside glass and synthetic polymers. Bones from domesticated animals could be mixed with batteries and construction fragments. This strange association might be more informative than any single artifact. It would reveal a species capable of moving material across continents and gathering it in enormous artificial deposits. Mines would leave deeper scars. Open pits already reshape entire landscapes. Underground tunnels extend through rock. Quarries remove hills. Oil and gas wells reach far below the surface. Some of these structures would collapse after humanity disappeared. Groundwater would fill them. Loose rock would fall inward. Vegetation would hide the entrances. Erosion would soften the edges of open pits. Given enough time, lakes might form inside them. Yet certain patterns could persist. Long, narrow boreholes might remain filled with material different from the surrounding rock. Tunnels could become compressed fractures. Entire ore bodies might appear strangely depleted. A future geologist could discover that valuable materials had been removed in a systematic way. Natural processes can concentrate and redistribute minerals, but industrial extraction follows economic patterns. Humanity removes particular elements from accessible regions, transports them, refines them, and spreads them across the surface. That movement is part of our planetary signature. Fossil fuels create an especially important change. Coal, oil, and natural gas formed from ancient carbon buried over immense periods. Human industry extracts that carbon and returns it rapidly to the atmosphere. This alters the balance of carbon isotopes. Atoms of the same element can have different numbers of neutrons. These different forms are called isotopes. Living organisms and geological processes do not always use all isotopes equally. As a result, different sources of carbon carry slightly different chemical signatures. Burning large quantities of fossil carbon changes the proportions preserved in the atmosphere, oceans, soils, and sediments. Future geologists may not discover an intact power station, but they could measure a sudden global shift in carbon chemistry. The signal would appear across many environments at approximately the same time. Ocean sediments, lake beds, cave formations, ice, soils. The civilization would be visible not as a structure, but as a planetary event. The atmosphere itself can become an archaeological record. Human activity releases greenhouse gases, industrial chemicals, and particles produced through combustion. Some remain for only short periods. Others alter global systems and leave indirect evidence behind. A rapid rise in temperature changes rainfall, glaciers, ocean circulation, and the habitats of living organisms. Species migrate, some populations grow, others decline or disappear. These biological changes enter the fossil record. Pollen preserved inside sediment can reveal changing vegetation. Shells record conditions in ancient oceans. The chemistry of tiny marine organisms reflects water temperature and acidity. Even when the original gases have vanished, the climate disturbance they caused may remain written into stone. Humanity is also transforming the movement of nitrogen. Nitrogen is essential for life, but most organisms cannot use the abundant nitrogen gas in the atmosphere directly. Industrial processes convert it into forms that crops can absorb. This supports large-scale agriculture and billions of people. Yet the added nitrogen also enters rivers, lakes, oceans, and soils. It changes ecosystems. It encourages rapid growth in some organisms and removes oxygen from certain waters when that organic matter decays. A future layer of sediment could contain evidence of this global disturbance. Phosphorus, another essential nutrient, is mined, concentrated into fertilizers, distributed across farmland, and carried into waterways. Together, these changes reveal a species reorganizing planetary chemistry to feed itself. Perhaps one of the clearest traces of humanity would be biological. Our civilization moves species across natural boundaries. Rats travel aboard ships. Insects cross oceans inside cargo. Plants are carried into new climates. Domesticated animals spread across continents. Crops once restricted to small regions are grown around the world. This creates a sudden mixing of ecosystems that evolved separately for millions of years. Future fossils might show the same small group of species appearing almost simultaneously in distant locations. The bones of cattle, pigs, chickens, dogs, and humans could become unusually widespread. Many wild species might decline at the same boundary. The signal would not look like a single extinction caused by an asteroid. It would show selection. Species useful to one technological organism would expand dramatically. Others would disappear as habitats changed. Human civilization could therefore be identified by the living world it reorganized. Yet even human bones would be rare. Billions of people are alive today, but most bodies will not become fossils. Burial customs may improve preservation in some environments. Coffins, tombs, and sealed chambers can protect remains for a time. But groundwater enters. Microorganisms act. Minerals dissolve and replace bone. Cemeteries are disturbed by erosion, construction, floods, and tectonic movement. Over millions of years, only a tiny fraction of human remains would likely survive in discoverable form. Our species may be globally dominant, but dominance does not guarantee a complete fossil record. Consider how little of an individual life becomes geological evidence. A person may live for decades. They may travel through many cities, write thousands of messages, create art, teach children, repair machines, and influence everyone around them. Yet after deep time, perhaps one tooth survives. Perhaps nothing survives. The experiences that define civilization are among the first things geology removes. Music leaves no fossil. Conversation leaves no mineral layer. Love, fear, ambition, humor, and memory cannot be directly preserved inside stone. A civilization is more than its material products, but only those products have a chance of entering the geological record. This creates an enormous silence. Future researchers might detect that humanity burned fossil fuels and produced artificial compounds. They might recognize that we altered the climate and moved species, but they may never know what we called ourselves. They may never hear our languages. They may not understand why we built cities or looked toward the stars. They could discover the shadow of our civilization without recovering its inner world. The same limitation would apply to any civilization before us. Suppose an intelligent species existed tens of millions of years ago. Its appearance might have been completely unlike ours. Its cities may have used materials that did not preserve well. Its technology might have relied on biology rather than metal. Perhaps it cultivated living structures that decomposed after abandonment. Perhaps its information was stored through chemical patterns inside organisms. Perhaps it lived mainly along coastlines, later destroyed by tectonic movement. Perhaps it never reached a population comparable to humanity. Perhaps its industrial period lasted only a few centuries. In such a case, the familiar evidence we expect might never have existed. There would be no stone skyscrapers, no satellites, no steel tools waiting inside caves. The civilization might still have changed its planet, but in ways difficult for us to recognize. We search through assumptions shaped by our own history. Because humans build with concrete and metal, we imagine that all technological beings would do the same. Because we use radio, we imagine that intelligence announces itself through radio signals. Because we store knowledge in writing, we search for inscriptions. But intelligence may produce many different solutions. An earlier Earth civilization, if one had existed, might leave evidence that does not resemble our idea of technology. The challenge is not only that evidence disappears, it may also become invisible to expectations. Scientists often discover important signals only after developing the correct question. A strange rock may remain ordinary until someone notices its chemistry. A fossil may be misunderstood until it is compared with a living organism. A thin sedimentary layer may appear unimportant until researchers connect it with a global event. The past does not explain itself. It waits for the present to learn how to read it. Still, there are limits to possibility. A large industrial civilization would require energy and resources. It would likely create waste heat. It would alter landscapes. It would concentrate materials. It might affect atmospheric chemistry. The larger and longer lived it became, the harder it would be for every trace to vanish. A civilization lasting millions of years would almost certainly leave substantial evidence. A short-lived civilization would be easier to hide, but it would also have less time to spread and transform the planet. This creates a balance. The more advanced and widespread the society, the stronger its geological signal should become. The smaller and briefer it is, the less likely we are to detect it. An earlier species could perhaps have formed towns, agriculture, and complex culture without becoming industrial. Such a society might leave little global evidence. Local sites could be destroyed or remain undiscovered. But a civilization using fossil fuels, mining continents, manufacturing synthetic materials, and altering the climate would be expected to create broader changes. The Silurian question therefore becomes one of scale. How many individuals existed? How long did they remain technological? What energy sources did they use? Where did they live? What materials did they produce? How much did they alter the atmosphere and oceans? Without answers to these questions, there is no single ancient signature to search for. There are only families of possible traces. Some might survive as objects, others as minerals, others as isotopic disturbances, others as changes in the living world, and some might not survive at all. For a moment, imagine standing on Earth 10 million years after humanity. The continents would still be recognizable, but their coastlines would have changed. Some modern cities would lie underwater. Others would be buried beneath river sediment. Mountain roads would have vanished. Forests and grasslands would cover regions once filled with farms. Most satellites would have fallen from orbit long before. Their fragments might burn in the atmosphere or scatter across land and sea. A small number placed in distant, stable orbits could remain longer, silently circling a planet that no longer remembered their builders. On the surface, no human voice would remain. No flag would move. No engine would start. Our monuments might be broken hills. Our tunnels might be flooded chambers. Our plastics might be altered particles inside rock. Our presence would be subtle, a thin boundary, a sudden chemical transition, a strange collection of bones and metals. The entire modern world, with its crowded streets and glowing screens, would become a geological puzzle. Now allow another 10 million years to pass, then 50 million, then 100 million. Continents would drift farther. New mountain ranges might rise. Old seas might close. Sedimentary layers containing our remains could be buried kilometers underground. Heat and pressure would transform them. Some would later rise and become exposed. Most would never be seen. The few surviving signs might appear in isolated cliffs, quarries, or drilling samples. A future intelligence could walk above one of our greatest cities without knowing it had ever existed. Beneath its feet, there might be only a compressed layer of unusual stone. This is what deep time does. It does not simply make the past older. It changes the form in which the past can be known. A city becomes rubble. Rubble becomes sediment. Sediment becomes rock. Rock is folded, buried, heated, lifted, and broken. Eventually, the original city survives only as chemistry and pattern can be difficult to distinguish from nature. This is why searching for an earlier civilization requires patience rather than excitement. There is no confirmed ancient artifact demanding an immediate rewriting of history. There is no hidden machine waiting in a museum basement. There is instead a quiet scientific question about preservation. How much of our world would remain? How would it appear? Could we recognize the same pattern if another species had created it long ago? The answer may be uncomfortable. Civilizations often imagine themselves as permanent. They build monuments, archives, and institutions intended to outlast generations. Yet on geological timescales, permanence becomes almost impossible. The planet does not preserve importance. It preserves what happens to enter the right environment. A common shell buried in ocean mud may survive longer than the most advanced computer ever built. A footprint made by an animal in wet sediment may outlast an entire nation. A layer of ash may remain readable when every book has vanished. Earth keeps no record of meaning. It keeps only matter, and matter is constantly changing. Still, complete erasure is difficult. Every action sends consequences outward. A road changes drainage. A dam traps sediment. A mine moves rock. A factory releases compounds. Agriculture changes soil. Transportation moves species. Even when the original action is forgotten, its effects can create new effects. Civilization spreads through the environment like a disturbance through water. The first waves are strong and obvious. Later waves weaken. Eventually, they become difficult to detect. But somewhere, in some form, the water remembers that it moved. Perhaps Earth remembers civilizations in the same way. Not with statues, not with names, not with intact machines, but with ripples preserved in stone, a change in carbon, a layer of unusual particles, a brief warming of ancient oceans, a sudden rearrangement of life. To know whether any such ripple came from intelligence, we must compare it with the powerful disturbances nature creates on its own. Because Earth has warmed before, its oceans have lost oxygen before, its atmosphere has changed before, species have vanished before. Volcanoes, asteroids, microbes, and shifting continents have rewritten the planet many times without technology. The next step in our journey is therefore more difficult. We must enter those ancient crises. We must examine moments when the planet changed with surprising speed, and we must ask whether any of them resemble the geological shadow our own civilization may leave behind. Not because resemblance proves that someone was here, but because, hidden among natural events, an artificial signal would need to speak the language of geology. A language without roads or ruins. A language made of isotopes, minerals, sediments, and time. For now, the abandoned city continues disappearing beneath the imagined forest. Rain falls through empty windows. Roots move through cracked foundations. Rivers carry fragments toward the sea. The towers become hills. The streets become soil. The machines lose their shapes. And after ages have passed, almost everything that once seemed permanent has been transformed. But not everything is gone. Deep beneath the quiet landscape, the planet has kept a faint record, not a portrait of the civilization, only its fingerprint. If an industrial civilization existed millions of years before humanity, its strongest surviving trace might resemble a climate catastrophe. It might appear as a rapid warming event, a disturbance in the carbon cycle, a decline in ocean oxygen, a sudden change in the types of organisms preserved in sediment. Perhaps a thin layer of unusual chemicals would mark the moment when that civilization expanded, consumed resources, and altered its atmosphere. The difficulty is that Earth has produced all of these signals naturally. Long before factories, engines, or power stations, the planet experienced periods of dramatic environmental change. Temperatures rose, oceans became acidic, large regions of the sea lost oxygen, carbon moved rapidly from underground reservoirs into the atmosphere. Species migrated, adapted, or disappeared. Some of these events unfolded slowly by human standards. Others were remarkably fast when measured against geological time. In the rocks, they can resemble the kind of disturbance humanity is creating today. This does not mean that ancient warming events were caused by civilizations. There is no accepted evidence that they were. Instead, their similarity reveals how difficult the search would be. Nature is capable of producing planetary changes that look almost technological. To distinguish intelligence from geology, scientists would need to understand both. One of the most studied examples occurred around 56 million years ago. It is known as the Paleocene-Eocene thermal maximum. The name is long, so researchers often shorten it to the PTM. At that time, the world was already warmer than it is today. Large ice sheets did not cover the poles in the way they do now. Forests extended into regions that are currently frozen. Crocodile-like animals lived at high northern latitudes beneath climates far milder than the modern Arctic. Then the planet warmed further. Across a relatively narrow geological interval, global temperatures increased significantly. The oceans absorbed large quantities of carbon dioxide. Their chemistry changed. Many marine organisms were affected. On land, rainfall patterns shifted, ecosystems moved, and some mammals became temporarily smaller. The event left a clear signal in sediments around the world. One of its most important features is a rapid change in carbon isotopes. The rocks show that a large amount of carbon entered the atmosphere and oceans. That carbon was unusually rich in the lighter isotope known as carbon-12. Fossil fuels also contain relatively large amounts of carbon-12 because they formed from ancient organic matter. When modern civilization burns coal, oil, and natural gas, it releases this light carbon into the atmosphere. As a result, the isotopic change humanity is creating shares a broad resemblance with the signal preserved during the PTM. This is one reason the event attracts so much attention. It provides a natural experiment from Earth's past. Scientists can study how climate, oceans, and ecosystems responded when large amounts of carbon entered the environment. But it also creates an intriguing challenge for the Silurian question. If researchers discovered the PTM without already knowing its likely natural causes, could they mistake it for industrial activity? At first glance, perhaps. There is rapid warming, a strong carbon isotope disturbance, ocean acidification, changes in life. These are signals an industrial civilization could produce. Yet the deeper record points toward natural explanations. Several possible sources of the carbon have been proposed. Volcanic activity may have played a major role. At the time, the North Atlantic region was being pulled apart as tectonic plates moved away from each other. Enormous quantities of magma entered Earth's crust. This activity could have heated organic-rich sediments, releasing carbon dioxide and methane. Volcanoes themselves may also have added greenhouse gases to the atmosphere. Warming could then have triggered additional releases from soils, oceans, frozen deposits, or other carbon reservoirs. The event may have involved several processes reinforcing one another. The exact sequence remains an area of scientific investigation, but nothing within the available evidence requires cities, machines, or industrial beings. The lesson is subtle. A geological signature may resemble technology while still being entirely natural. Earth's systems are interconnected. A change beginning deep underground can move through the atmosphere, oceans, climate, and biosphere. The final result can appear coordinated because the entire planet responds together. Intelligence is not required for global consequences. Another dramatic event occurred much earlier, around 200 million years ago, near the boundary between the Triassic and Jurassic periods. At this time, most of Earth's continents were joined within the supercontinent Pangaea. The Atlantic Ocean had not yet opened into its modern form. Then enormous volcanic eruptions began across a region that would eventually become parts of North America, South America, Africa, and Europe. These eruptions formed what geologists call the Central Atlantic Magmatic Province. Lava spread across vast areas. Magma entered the crust. Greenhouse gases entered the atmosphere. Climate changed. Ocean chemistry was disturbed. A major extinction followed. Many groups of organisms disappeared, while dinosaurs survived and later became dominant across terrestrial ecosystems. In the geological record, the event includes rapid carbon cycle changes and repeated volcanic pulses. Again, some features might superficially resemble the effects of an industrial civilization. Large amounts of carbon entered the atmosphere. Temperatures increased. Ecosystems collapsed. The chemistry of the planet shifted. But the rocks also contain evidence of immense volcanism. Layers of lava remain. Mineral dating connects the eruptions with the environmental crisis. The scale of the volcanic province is difficult to imagine. This was not one mountain erupting for several days. It was a prolonged episode in which magma repeatedly reached the surface across an enormous region. Nature can release carbon on a planetary scale. It can transform climate without a single engine. The end of the Permian period offers an even more extreme example. Around 252 million years ago, Earth experienced the largest known mass extinction in the fossil record. A very large proportion of marine species disappeared. Terrestrial ecosystems were devastated. Forests declined across many regions. Food webs collapsed. For life on Earth, it was one of the darkest transitions ever preserved. The crisis is strongly associated with colossal volcanic activity in what is now Siberia. The resulting rock formation is known as the Siberian Traps. The word traps comes from a term meaning steps, referring to the layered appearance of the solidified lava. These eruptions released enormous amounts of volcanic material over a long period. Carbon dioxide warmed the climate. Sulfur compounds may have caused episodes of cooling and acid rain. Magma heating underground deposits may have released additional greenhouse gases. Oceans became warmer and more acidic. As warm water holds less oxygen, large marine regions became increasingly difficult for animals to survive in. Ocean circulation may have weakened. Toxic conditions may have spread. The extinction was not caused by one simple mechanism. It emerged from interacting stresses: heat, acidity, low oxygen, habitat disruption, possibly toxic gases, changes in nutrient cycles. The planet's systems moved into a dangerous state, and life suffered across land and sea. If a future geologist examined only a small part of this boundary, the pattern could appear mysterious. There might be abrupt warming, carbon changes, unusual metal concentrations, a collapse in biodiversity, sediments formed beneath oxygen-poor water. Without broader context, these signals might invite extraordinary interpretations. But when researchers assemble evidence from many locations, the volcanic explanation becomes far stronger. This shows why isolated anomalies are not enough. A strange chemical layer may seem artificial when viewed alone. Yet science gains reliability by connecting different forms of evidence. Do volcanic rocks appear at the same time? Do isotope changes match gases expected from magma or heated sediments? Did the event unfold gradually or in repeated pulses? Was it global or regional? Do ocean and land records tell the same story? Is there a known tectonic event capable of producing the observed effects? A civilization hypothesis would need to explain the entire pattern better than geology does. So far, none of Earth's ancient crises requires such an explanation. Volcanoes are not the only natural source of sudden disruption. Asteroid impacts can also alter the entire planet. Around 66 million years ago, a large asteroid struck near the region now occupied by the Yucatan Peninsula. The impact released extraordinary energy. Rock vaporized. Earthquakes moved through the crust. Large waves crossed the oceans. Material was thrown high into the atmosphere. Fine particles and aerosols reduced the sunlight reaching the surface. Temperatures changed. Photosynthesis declined. Food chains collapsed. The event contributed to the extinction of the non-avian dinosaurs and many other groups. The impact left several distinct clues. There is a global layer enriched in iridium, an element that is relatively rare in Earth's crust, but more common in some asteroids. Shocked minerals record extreme pressures. Tiny droplets of once molten rock appear within sediments. And beneath the Yucatan lies the enormous Chicxulub crater. Together, these signals form a coherent story. An unusual metal layer alone might have looked like industrial contamination. But the crater, shocked minerals, and impact debris point overwhelmingly toward a natural collision. Again, context transforms mystery into explanation. The biosphere itself can create global change. Life is not merely a passenger on Earth. It alters the atmosphere, rocks, soils, and oceans. The most dramatic example began billions of years ago, when microorganisms capable of oxygen-producing photosynthesis became widespread. These organisms used sunlight to extract energy. They released oxygen as a byproduct. At first, much of that oxygen reacted with iron dissolved in the oceans and with other materials on Earth's surface. Layer by layer, iron minerals accumulated on the seafloor. Eventually, oxygen began increasing in the atmosphere. For many organisms alive at the time, oxygen may have been toxic. Entire ecosystems based on oxygen-free chemistry were forced into shrinking habitats. Yet for later life, oxygen opened new possibilities. It allowed more efficient forms of metabolism. It contributed to the formation of an ozone layer that reduced harmful ultraviolet radiation at the surface. The atmosphere was transformed by microscopic organisms with no intelligence and no plan. If an observer had watched Earth from a great distance, the change might have resembled planetary engineering. A new gas accumulated globally. Ocean chemistry shifted. Minerals changed. Existing organisms were disrupted. New forms of life emerged. The planet gained a powerful atmospheric biosignature, but the engineers were bacteria. Their technology was photosynthesis, developed through evolution rather than conscious design. This reminds us that biological activity can imitate some effects associated with civilization. A species does not need factories to transform a world. It may only need a new metabolism and enough time. Plants later changed the continents. Before complex vegetation spread across land, much of Earth's surface lacked deep soils held together by roots. As plants expanded, they broke down rock, altered rivers, changed erosion, stored carbon, and created new habitats. Forests affected rainfall and atmospheric chemistry. The development of roots changed how sediment moved from continents into oceans. Earth's geological record carries the signature of these living innovations. A future researcher unfamiliar with plants might find the changes abrupt and strange, yet they arose naturally from evolution. This is one of the deepest challenges in identifying ancient intelligence. Technology is not the only process capable of changing a planet quickly. Evolution creates innovations. Geology releases stored energy. Climate systems contain feedback loops. Oceans shift between different states. When these processes interact, the results may appear almost purposeful. The oceanic anoxic events preserved in ancient rocks provide another example. During several periods of Earth's history, large portions of the oceans became depleted in oxygen. In oxygen-poor water, many ordinary organisms struggle to survive. Decomposition changes. Organic matter can accumulate on the seafloor rather than being fully broken down. Dark, carbon-rich sediments may form. Some of these layers later become sources of oil and natural gas. Oceanic anoxic events are often connected with warm climates, volcanic activity, changes in nutrient supply, and altered ocean circulation. If volcanoes release carbon dioxide, temperatures rise. Warmer water holds less dissolved oxygen. Increased rainfall can carry more nutrients from land into the sea. Microscopic organisms grow rapidly near the surface. When they die and sink, bacteria consume oxygen while decomposing them. If ocean circulation cannot replace that oxygen quickly enough, deep waters become suffocating. The process can expand across vast regions. A technological civilization could also create low-oxygen waters. Modern agriculture releases nitrogen and phosphorus into rivers and coastal seas. These nutrients encourage algal blooms. When the algae die, decomposition removes oxygen. Dead zones form. Industry and climate warming can intensify the problem. Therefore, an ancient layer created during widespread ocean anoxia could resemble the consequences of agriculture and industrial warming. But again, geological evidence often points toward natural triggers, such as large volcanic provinces. The similarity is informative, not incriminating. It teaches us which signals are ambiguous. Carbon disturbances are ambiguous. Rapid warming is ambiguous. Ocean anoxia is ambiguous. Extinction is ambiguous. Metal enrichment may be ambiguous. Even unusual sedimentation can have many causes. To make a persuasive case for ancient industry, scientists would need something more specific. They would search for combinations that nature is unlikely to create together. Artificial molecules could be especially valuable. Modern civilization manufactures compounds that did not previously exist in significant quantities. Some are designed to resist heat, water, chemical reactions, or biological decay. Plastics are the most familiar example. They are made from long chains of molecules called polymers. Natural polymers exist everywhere. Wood, proteins, DNA, and the shells of some organisms are all based on repeating molecular structures. But industrial plastics have distinctive arrangements and additives. Could they survive for millions of years? Many plastic objects would eventually fragment. Sunlight breaks chemical bonds. Heat changes molecular structures. Microorganisms may slowly adapt to use some compounds. Pressure and burial transform materials. After deep time, a plastic bottle would probably not remain a clear plastic bottle, yet some chemical products of its breakdown might persist. Microscopic particles could become incorporated into sediment. Under heat and pressure, plastics might transform into carbon-rich films or unfamiliar hydrocarbons. The challenge would be recognizing their artificial origin after those changes. A compound that appears obviously manufactured today may become chemically simple after millions of years. Its history would be hidden within its structure. Persistent industrial pollutants could leave longer-lasting signals. Certain synthetic chemicals resist natural breakdown. Some accumulate inside organisms and sediments. But even these compounds are not permanent on geological timescales. Their molecular bonds can be altered. They may react with minerals. They may be buried, heated, and transformed. Future scientists studying humanity might detect their descendants rather than the original chemicals. Identifying an ancient civilization could therefore require predicting how artificial materials change through deep time. Scientists would need to manufacture substances, expose them to pressure and temperature, and study what remains. They would ask not only what modern industry produces, but what those products become after 1 million, 10 million, or 100 million years. The search might focus on unusual molecular arrangements, patterns of carbon that biological and geological processes rarely produce, persistent combinations of elements, microscopic structures showing repeated manufacturing. But nature is inventive. Some crystals grow into geometric forms, minerals create fibers and layers. Chemical reactions produce spheres, tubes, and complex branching shapes. Natural processes can generate objects that look designed. Researchers studying possible ancient technology would need to resist the human tendency to see intention inside coincidence. Radioactive materials might offer another clue. Nuclear technology changes isotopes in distinctive ways. Reactors produce elements and isotope ratios that are rare in nature. Nuclear explosions distribute radioactive material across wide regions. Some isotopes decay quickly, others remain detectable for much longer. After millions of years, most short-lived radioactive products would vanish, but their decay could create stable daughter elements in unusual proportions. Materials stored deep underground might also survive if geological conditions remained favorable. However, even nuclear signatures require caution. Natural nuclear reactors have existed on Earth. Around 2 billion years ago, deposits of uranium in what is now Gabon achieved conditions that allowed sustained nuclear fission. Groundwater moved through uranium-rich rock. The natural concentration of uranium-235 was higher at that time than it is today. Under the right circumstances, the deposits behaved like reactors. The reactions continued intermittently for long periods. When scientists discovered the isotope patterns, they recognized that nuclear fission had occurred naturally. This is an extraordinary example of Earth imitating technology, a process associated in the modern world with carefully engineered facilities once happened underground without intelligence. Therefore, even evidence of nuclear reactions would not automatically prove civilization. Researchers would need to study the geometry, byproducts, location, and surrounding materials. Was the reaction organized in a way consistent with engineering? Or could groundwater and mineral concentration explain it? The distinction between nature and technology may be less obvious than it first appears. Nature performs chemistry. It builds structures. It stores energy. It creates feedback systems. It even produces forms of selection and information through life. Technology uses the same physical laws. It does not introduce magic into the universe. It rearranges matter through intention. The evidence of intelligence lies not in the materials themselves, but in the improbable patterns created from them. A piece of refined metal is still made of natural atoms. A computer chip contains elements found in rock. A plastic object is assembled from carbon and hydrogen. What makes these objects technological is arrangement. The atoms are placed into forms unlikely to arise through ordinary processes. But deep time destroys arrangement. A circuit board corrodes, a machine collapses, a building becomes sediment. As organization disappears, technology becomes increasingly difficult to distinguish from nature. This may be the central problem of the Silurian hypothesis. Civilization produces order, geology gradually removes it. What remains is the chemical residue of once organized matter, and chemistry can often be explained in more than one way. Perhaps the most convincing ancient signature would involve several independent anomalies occurring together. Imagine a narrow sedimentary boundary containing a rapid carbon isotope shift. At the same moment, there is evidence of warming and ocean acidification. Unusual concentrations of refined metals appear globally. Synthetic molecular remnants are detected in both marine and continental deposits. The fossil record shows a sudden spread of a small group of domesticated species. There is evidence of mining, rapid erosion, and artificial radioactive products. No volcanic province, asteroid impact, or known biological innovation explains the entire pattern. Such a discovery would deserve extraordinary attention. It still would not prove civilization immediately. Researchers would test every natural alternative. Samples would be collected from many locations. Laboratories would attempt to reproduce the chemical signals. Dating methods would be checked. Contamination would need to be ruled out. The history of science contains many exciting claims that weakened under further study. A signal buried for millions of years would demand exceptional care. Modern contaminants can enter ancient rock. Drilling equipment introduces materials. Groundwater moves chemicals through cracks. Samples may be mishandled. The more extraordinary the conclusion, the more carefully every ordinary explanation must be examined. This caution is not an attempt to avoid discovery. It is how genuine discovery survives. If evidence of an earlier civilization were real, careful testing would make the case stronger. But so far, no ancient geological boundary contains the complete pattern needed. Earth's crises appear understandable through natural processes. The PTM can be studied through carbon release and climate feedbacks. The end Permian extinction aligns with enormous volcanism and cascading environmental stress. The end Cretaceous extinction carries the unmistakable evidence of an asteroid impact. Oceanic anoxic events connect with climate, nutrients, circulation, and volcanic activity. These explanations may still contain unanswered details, but unanswered details are not evidence of technology. Mystery is not the same as artificiality. This distinction matters because human imagination naturally enters gaps. When the record is incomplete, stories rush forward to fill it. A strange layer becomes a destroyed city. An unusual fossil becomes an engineered organism. A rapid climate event becomes industrial collapse. Such possibilities may be fascinating, but science asks a quieter question. What explanation requires the fewest unsupported assumptions, while accounting for the most evidence? At present, the answer remains nature. Earth is capable of producing extraordinary change without civilization, yet the comparison is still valuable. When scientists place humanity beside ancient climate events, they learn how unusual our present moment may appear in future rocks. Our carbon emissions are occurring rapidly. Our materials are spreading globally. Our influence reaches from the atmosphere to the deep ocean. We are becoming a geological force. The ancient events act as mirrors. They show what can happen when carbon enters the atmosphere, temperatures rise, and oceans lose oxygen. They also show that recovery may require immense amounts of time. A climate disturbance lasting thousands of years may be brief geologically, yet overwhelming for civilizations and ecosystems living through it. Rock layers compress suffering. A few centimeters of sediment may represent generations of ecological disruption. From the distant future, the event may look like a sharp line. For those inside it, the change unfolds across entire lives. Perhaps this is why the Silurian hypothesis feels unsettling. It asks whether another civilization could have vanished, but it also asks what kind of layer humanity is creating now. Suppose our industrial period ends after only a few centuries. Future rocks might show a sudden release of fossil carbon, rapid warming, ocean acidification, changes in nitrogen and phosphorus, plastic particles, industrial metals, radioactive traces, a mass movement of species. Then the signal may stop. To a future geologist, it could resemble a brief fever in the planet. They might infer that something unusual happened. Whether they would recognize civilization is uncertain. Perhaps they would see only a carbon event. Perhaps they would debate volcanic activity. Perhaps our artificial materials would provide the missing clue. Or perhaps erosion and burial would hide the most important evidence. The question returns in a new form. If we could misunderstand the traces of our own civilization after deep time, might we misunderstand something already buried? Possibly. But possibility must remain separate from probability. The geological record contains no confirmed sign of pre-human industry. The known evolution of complex intelligence points toward humanity as the first species on Earth to develop global technological civilization. Earlier animals were remarkable, but none left evidence of manufacturing, large-scale mining, controlled energy systems, or planetary industry. Still, the record is incomplete, and incompleteness invites careful investigation, not belief, not dismissal. Investigation. The rocks do not need to hide a civilization for the question to be useful. By asking what artificial planetary change would look like, scientists become better at recognizing both technology and nature. They learn which biosignatures may be misleading. They improve the search for life on exoplanets. They consider how an alien industry might alter atmospheric gases. They examine whether pollutants, artificial illumination, or unusual heat patterns could be detected from far away. Earth becomes a laboratory for worlds we cannot visit. The ancient climate crises become examples of false positives. A distant planet may contain methane and carbon dioxide because life is active, or because volcanoes are releasing gases. It may show unusual atmospheric chemistry because technology is present, or because a new metabolism has transformed the biosphere. A sudden change may indicate intelligence or a natural tipping point. The lesson is humility. The universe rarely provides labels. Evidence arrives as light, chemistry, motion, and pattern. Interpretation requires patience. Here on Earth, ancient sediments preserve moments when the world changed rapidly. Some appear strangely familiar. Warm oceans, rising carbon, declining oxygen, disappearing species. But beneath the resemblance lies a deeper truth. A planet does not need a civilization to enter crisis. It only needs enough energy, enough carbon, and a system capable of amplifying change. Volcanoes can begin the disturbance. Oceans can strengthen it. The atmosphere can carry it around the world. Life can respond in ways that create new feedbacks. The result becomes a global event written across stone. There may be no intention, no machines, no one watching. Only physics, chemistry, biology, and time. As night settles over the modern world, our own cities continue glowing. Power moves through cables, aircraft cross the sky, factories reshape raw materials. Invisible gases enter the atmosphere. Rivers carry the chemical products of agriculture toward the sea. Our civilization leaves traces every moment. Some resemble ancient natural events. Others may be entirely new. Future geology will separate them only if enough evidence survives. And somewhere beneath us, older boundaries wait in darkness. Each marks a world that changed. A warming, an extinction, an ocean without oxygen, a sky filled with volcanic gases. They may feel like echoes of civilizations that never existed. Warnings written by nature long before anyone was present to read them. The deeper mystery is not whether every ancient catastrophe hides intelligence. It does not. The deeper mystery is how easily the consequences of intelligence can resemble a catastrophe, and how quickly a civilization, once reduced to chemistry, may become indistinguishable from the restless planet that buried it. To search for a forgotten civilization, we must first imagine the beings who might have created it. They would not necessarily resemble us. They might not walk upright. They might not possess faces we could easily recognize. Their bodies would have been shaped by a world belonging to another age, beneath unfamiliar constellations and across continents that no longer exist. Yet a civilization requires more than an unusual body. It requires a particular gathering of abilities: memory, communication, curiosity, cooperation, the manipulation of objects, the transmission of knowledge from one generation to the next, and perhaps most importantly, the ability to accumulate discoveries rather than beginning again each time an individual dies. Earth has produced many intelligent animals, but only one known species has created global industry. This difference raises a difficult question. Is technological civilization the expected result of intelligence, or is humanity the outcome of an extraordinarily rare sequence of accidents? For a long time, people imagined evolution as a ladder. Simple organisms occupied the bottom. Complex animals stood above them. Humans waited at the top. From this perspective, intelligence appeared to be the destination toward which life was slowly traveling. Given enough time, it seemed that evolution would eventually produce something like us. Modern biology offers a different picture. Evolution has no final destination. It does not look ahead. It does not decide that a species should become intelligent, upright, or technological. It changes populations according to the pressures surrounding them. A trait survives when it helps organisms reproduce within a particular environment. Sometimes greater intelligence is useful. Sometimes it is expensive and unnecessary. Brains require energy. They take time to develop. Young animals with large and complex brains may need long periods of care. Learning creates flexibility, but instinct can solve many problems more quickly and at lower biological cost. A shark does not need to understand engineering to survive successfully in the ocean. An insect colony can build elaborate structures without any individual understanding the entire design. A tree can dominate a landscape while possessing no nervous system at all. Evolution rewards survival, not philosophical depth. Technology is therefore not guaranteed. For most of Earth's history, life remained microscopic. Single-celled organisms transformed oceans, soils, minerals, and the atmosphere. They survived conditions that would destroy almost every large animal alive today. They spread through nearly every environment where liquid water and usable energy existed. By any biological measure, microorganisms were extraordinarily successful, yet they never built cities. Complex animals appeared much later. Over hundreds of millions of years, nervous systems became more varied. Eyes evolved in different forms. Predators learned to follow prey. Prey learned to hide, escape, cooperate, and deceive. Memory became increasingly valuable. So did the ability to adapt behavior when familiar strategies failed. The ancient world slowly filled with animals capable of sensing, deciding, and learning. But how close did any of them come to civilization? Dinosaurs naturally occupy the center of this mystery. Non-avian dinosaurs lived on Earth for an immense stretch of time. Their history lasted far longer than the entire existence of our species so far. They spread across every continent. They evolved into enormous herbivores, armored forms, horned animals, swift hunters, feathered predators, and eventually birds. Some cared for nests. Some traveled in groups. Some possessed sharp vision and highly developed senses. Their world was not populated by slow, simple monsters. It contained animals adapted to complex ecological relationships. Yet intelligence cannot be measured easily in an extinct creature. Brains almost never fossilize. Paleontologists usually study the internal spaces of skulls, producing models called endocasts. These can reveal the approximate shape and size of the brain cavity. They may offer clues about regions connected with smell, vision, balance, or hearing. But they cannot show thoughts. They cannot reveal language, imagination, social traditions, or the ability to plan far into the future. Even among living animals, intelligence is difficult to reduce to one measurement. A larger brain does not automatically mean a more intelligent animal. Body size matters. The organization of the brain matters. The density and arrangement of neurons matter. The animal's senses, environment, social behavior, and life history also matter. Some small predatory dinosaurs, known as troodontids, had relatively large brains for their body size. They possessed forward-facing eyes that may have provided good depth perception. Their hands included fingers capable of grasping. Some had delicate bodies, long legs, and sensory abilities useful for hunting in dim conditions. Because of these features, they are sometimes presented in popular culture as the most intelligent dinosaurs. But the phrase can be misleading. Being among the most intelligent dinosaurs does not mean possessing human-like intelligence. A troodontid may have been alert, adaptable, and behaviorally sophisticated. It may have learned from experience. It may have cared for offspring, or used complex hunting strategies. None of this means that it was approaching mathematics, writing, or industry. There is an enormous distance between solving ecological problems and constructing a civilization. In the early 1980s, paleontologist Dale Russell participated in a famous thought experiment. He imagined what might have happened if a troodontid lineage had survived the extinction at the end of the Cretaceous and continued evolving toward greater intelligence. The speculative creature became known as the dinosauroid. It was shown standing upright, with a large head, human-like proportions, and hands capable of delicate manipulation. The model became memorable because it gave visual form to an irresistible idea. Perhaps, without the asteroid, dinosaurs would eventually have created their own version of humanity. Yet the dinosauroid also revealed how easily imagination follows familiar paths. Why should an intelligent dinosaur become humanoid? Why should its body straighten in the same way as ours? Why should its face, hands, and posture converge upon the human form? Evolution does not necessarily repeat the same design. An intelligent descendant of dinosaurs might have remained horizontal. It might have used a beak and feet to manipulate objects. It might have possessed feathers for communication. Its intelligence could have been social, visual, or spatial in ways difficult for humans to imagine. The human body is not the universal shape of thought. Modern birds make this clear. Birds are living dinosaurs. They descended from feathered theropods and survived the extinction that ended all other dinosaur lineages. Some living birds display remarkable cognitive abilities. Crows and ravens can solve multi-step problems. They remember individual faces. They hide food and sometimes alter their behavior when they know another animal has been watching. Parrots can learn categories, imitate sounds, and associate signals with objects or actions. Some birds manufacture or modify tools. Others pass learned behaviors through groups. A bird's brain is organized differently from a mammal's, yet it can still support flexible and complex behavior. This tells us that advanced cognition did emerge within the dinosaur lineage. It did not produce an industrial civilization, but it demonstrates that intelligence was not restricted to mammals. Long before humans appeared, the evolutionary foundations of sophisticated behavior were already present in other branches of life. Could one of those branches have gone farther and then disappeared? In principle, evolution allows many possibilities. In evidence, however, the answer remains quiet. No dinosaur fossil has been found beside a manufactured tool that can be reliably attributed to it. No ancient quarry shows systematic dinosaur mining. No geological layer from the Mesozoic contains a confirmed global pattern of artificial materials, industrial pollution, or energy use. No fossilized settlement has been discovered. The record contains nests, eggs, footprints, feeding marks, injuries, and traces of movement. It reveals animals living remarkably complex lives, but it does not reveal industry. Perhaps a civilization might have been too small to leave a global signal. A local culture using wood, fiber, bone, and other fragile materials could vanish almost completely. Imagine a population of intelligent animals living beside a river. They shape sticks into tools. They build shelters from branches. They use stones to open food. They communicate through calls and gestures. Older individuals teach the young. Over generations, their techniques become more refined. This would be a form of culture, but it might leave almost nothing after millions of years. Wood decays. Fibers disappear. River channels move. The bones and stone fragments become scattered. Paleontologists discovering the site might never realize that learned traditions existed there. Civilization is not the same as intelligence, and intelligence is not the same as culture. These stages can exist separately. Many animals learn from one another. Some traditions remain within groups for generations. Songs, migration routes, hunting techniques, and tool use behaviors can be socially transmitted. But cumulative culture is different. It allows discoveries to build upon earlier discoveries. One individual makes a simple improvement. Another preserves it and adds something new. The next generation begins not at the original starting point, but from the improved version. Over time, small changes accumulate into technologies no single individual could invent alone. A modern computer was not created by one isolated mind. It depends upon centuries of mathematics, metallurgy, physics, chemistry, manufacturing, and shared information. Human civilization is built from knowledge stacked across generations. This stacking process may be one of the rarest steps in the rise of technology. An intelligent animal could solve difficult problems while remaining unable to preserve solutions beyond its immediate group. It might communicate, yet lack a language precise enough to describe invisible ideas. It might use tools, yet fail to improve them gradually. It might learn, but possess a lifespan too short for extensive teaching. It might be highly social, but live in an environment where discoveries are difficult to store. The difference between a clever species and an industrial species may depend less on raw intelligence than on the stability of cultural memory. Humans preserve ideas outside the brain. A spoken story allows information to survive the person who first experienced it. A drawing stores shape. Writing stores language. Mathematics stores relationships. A library allows a mind to learn from people who died thousands of years earlier. External memory changes the speed of civilization. Once information can be recorded reliably, knowledge grows beyond the capacity of any individual. Did any earlier species create external memory? There is no evidence that it did. But we should remember how fragile early records can be. Marks scratched into bark would disappear. Patterns arranged in leaves would vanish. Knotted fibers could decay. Pigments exposed to weather might last only briefly. A symbolic culture could exist without leaving inscriptions in stone. Yet the longer and more widespread such a culture became, the greater the chance that some durable evidence would survive. Humans used stone tools for millions of years before industry. Those tools remain because stone can preserve intentional shapes. Archaeologists identify repeated patterns. They see where flakes were removed. They compare objects across sites. They recognize that the forms were produced by controlled action rather than random breakage. If an earlier species had manufactured stone tools extensively, we might expect at least some examples to exist. None have been confirmed from times preceding known tool-making hominins. The silence does not prove that no animal ever held a stone with purpose. Many probably did. It suggests that no earlier lineage created a widespread stone technology comparable to that of our ancestors. The rise of humans required a rare combination of traits. Our ancestors lived on land, where fire could be controlled. They had hands capable of delicate and powerful grips. They walked upright, freeing those hands for carrying and manipulation. They lived in social groups where cooperation and competition both rewarded mental flexibility. They developed increasingly complex communication. Their long childhoods provided time for learning. They consumed energy-rich food that helped support costly brains. And they occupied changing environments where behavioral adaptability offered an advantage. None of these traits alone created civilization. Together, over immense periods, they produced a pathway. Fire may have been especially important. It provided warmth and protection. It transformed food, making some nutrients easier to absorb. It extended activity into the night. Eventually, controlled heat allowed clay to be fired and metals to be extracted from ore. Without high temperatures, many forms of technology remain impossible. This creates a major barrier for intelligent life in the oceans. The sea contains some of Earth's most cognitively remarkable animals. Dolphins cooperate, communicate, play, and maintain complex social relationships. Whales transmit songs and migration traditions across generations. Octopuses solve problems, explore unfamiliar objects, escape enclosures, and manipulate their surroundings with extraordinary flexibility. An octopus appears almost designed for tool use. Its arms are flexible. Its suckers can touch, taste, grip, and investigate. It can squeeze through narrow openings. It can manipulate stones, shells, and other objects. Some octopuses have been observed carrying coconut shell halves and assembling them into shelter. This behavior is especially interesting because the shells are transported for later use. The object provides no immediate benefit while it is being carried. It becomes useful only when reassembled. This resembles a simple form of preparation. Yet octopuses face limitations very different from our own. Many species live relatively short lives. Adults may die after reproducing. This reduces opportunities for parents to teach offspring over long periods. Many octopuses are also solitary. A discovery made by one individual may never spread widely. Their bodies contain few hard parts, making fossil preservation difficult, and their underwater environment prevents ordinary fire. An octopus could be capable of understanding that a rock contains metal without having an easy way to smelt the ore. It could arrange objects with great skill while remaining unable to generate the controlled heat needed for ceramics, glass, or metallurgy. This does not make underwater civilization logically impossible. An aquatic species might discover chemistry that does not require flame. It could use geothermal vents. It might cultivate organisms to produce useful materials. It could build through shells, minerals, adhesives, or living tissue. Its technology might follow a path almost unrecognizable to humans. But reaching high-energy industry beneath water would be challenging. Technology develops from available opportunities. Humanity's path relied heavily upon combustion. Wood burned, charcoal burned hotter, ores entered furnaces, steam moved machinery, fossil fuels powered engines. An underwater species would need an alternative ladder. Dolphins and whales face another obstacle. They possess sophisticated social intelligence, but their bodies are not suited to fine manipulation. A dolphin can move objects with its mouth or body. It cannot hold several small components and assemble them with fingers. Its intelligence may support communication, alliances, teaching, play, and emotional complexity without producing physical technology. This is an important reminder. Mental sophistication does not guarantee engineering. A species may possess a rich inner world while leaving almost no manufactured objects. If whales disappeared, future paleontologists could study their skeletons. They might examine the structures associated with hearing. They might infer that the animals communicated through sound. But would they know that some whale populations possess distinct songs? Would they discover traditions transmitted across generations? Would they recover the social relationships that shaped entire lives? Probably not. The fossil record captures anatomy more easily than culture. An ancient intelligent lineage could therefore be hidden in plain sight. Its bones might already be known. Its behavior might remain invisible. Perhaps one extinct animal communicated symbolically. Perhaps another recognized itself and imagined future events. Perhaps a species possessed traditions more elaborate than anything observed in modern wildlife. Unless those abilities created durable physical patterns, paleontology might never detect them. This possibility is far more plausible than a vanished industrial civilization. Complex cognition can leave little geological evidence. Industry is more difficult to hide. The original Silurian hypothesis was designed around this distinction. It does not ask whether another animal was clever. Earth certainly produced many forms of intelligence. It asks whether an energy-intensive industrial civilization could have existed and then become nearly invisible within the geological record. This means that an earlier species would need to cross several thresholds. First, it would require flexible intelligence, then communication, then cumulative culture, then durable external memory, then technologies capable of accessing greater amounts of energy, then the extraction and transformation of planetary resources. Each threshold is difficult. Many species may reach the first, fewer reach the second in complex forms. Some demonstrate culture. Only humans are known to have crossed the entire sequence. The path may not be a smooth staircase. Progress can reverse. A species may lose abilities when environments change. A small intelligent population can disappear through disease, competition, or climate disruption. A cultural tradition can end when the individuals who know it die. Technologies require networks. Minds depend upon transport. Transport depends upon infrastructure. Infrastructure depends upon social coordination. If those connections break, complex systems can collapse. An early civilization might rise only part of the way. It could develop agriculture without metallurgy, cities without fossil fuels, symbolic communication without machines. Such societies would leave regional evidence rather than a global atmospheric signal. After tens of millions of years, that evidence might be extraordinarily difficult to locate. But again, there is no positive evidence that such a society existed before humanity. The possibility lives inside the gaps, not inside discoveries. Science must treat gaps carefully. An incomplete fossil record means we do not know everything. It does not mean that every imagined event becomes equally likely. Still, ancient life is not entirely unknowable. Fossils reveal delicate feathers. They preserve stomach contents. They record footprints, nests, skin impressions, burrows, and diseases. Some deposits capture entire ecosystems with remarkable detail. If a widespread civilization had manufactured durable objects, altered landscapes, or concentrated materials across continents, at least part of that activity might be expected to survive. The absence of such evidence matters. It does not create absolute certainty, but it lowers the probability. The most reasonable conclusion remains that no industrial civilization existed on Earth before humans. This conclusion is not based simply on the absence of a buried city. It rests upon the combined history of life, tools, geology, and planetary chemistry. Complex organisms existed for hundreds of millions of years. Some developed impressive cognition, but the known record shows no gradual emergence of prehuman manufacturing. No unexplained technological horizon interrupts dinosaur history. No artificial transition appears among ancient marine sediments. The world before humanity appears biologically rich, behaviorally complex, and entirely non-industrial. Yet the evolutionary question continues to fascinate because intelligence has appeared more than once. Primates evolved flexible cognition. Birds evolved it through a different neural architecture. Cetaceans evolved it in the sea. Cephalopods evolved it along a path separated from vertebrates by an enormous evolutionary distance. Nature seems capable of discovering intelligence repeatedly. What it has not repeatedly produced, as far as we know, is industry. Perhaps intelligence is common while civilization is rare. Perhaps many species become aware of their surroundings but never reshape the planet. They may communicate, they may remember, they may grieve, they may solve problems and recognize companions. They may possess experiences as real and vivid as our own, yet they leave no cities. This possibility changes the way we think about extraterrestrial life. A distant planet could contain oceans filled with intelligent beings that never transmit radio signals. A forest world could support animals with complex cultures but no metallurgy. A moon beneath an icy shell might contain minds that never see the stars. The universe could be rich in awareness and still appear technologically silent. Here on Earth, perhaps intelligence flickered many times without becoming civilization. A clever predator watches movement through an ancient forest. A social animal remembers every member of its group. A marine creature manipulates shells beneath a vanished sea. A bird-like dinosaur learns routes, calls, and strategies from its parents. None builds a machine. None changes atmospheric chemistry. None leaves a signal visible millions of years later. Their thoughts vanish with them. This is one of deep time's greatest losses. Bones may fossilize, minds do not. We can reconstruct muscles from scars on bone. We can estimate vision from the shape of an eye socket. We can infer hearing from structures within a skull. But no fossil preserves a dream. No mineral records curiosity. A species may have looked into the night sky long before humans, aware of the lights above without understanding what they were. It may have experienced wonder. There would be no geological method for proving it. Civilization leaves matter. Consciousness leaves almost nothing. The mystery of earlier intelligence is therefore wider than the Silurian hypothesis. There may never have been an earlier industrial society, but Earth could have contained forms of awareness far richer than the surviving record reveals. Entire mental worlds may have appeared and disappeared. Languages without writing. Traditions without monuments. Knowledge carried only inside living brains. When the species vanished, its invisible culture vanished with it. Perhaps some behaviors survived through descendants. Birdsong may carry ancient patterns. Animal migrations may follow routes learned over countless generations. Instinct and culture flow together in ways that are difficult to separate. The past may still move through living creatures, not as a remembered civilization, but as inherited responses shaped by worlds that no longer exist. And humanity itself is connected to this long history. Our intelligence did not appear suddenly from lifeless material. It grew from older abilities: attention, memory, social bonding, tool use, imitation, play, fear, curiosity. These existed in various forms before our species. Civilization assembled them into something new. It created a system in which knowledge could grow faster than biology changed. Genetic evolution shaped the human brain slowly. Cultural evolution then began transforming behavior with extraordinary speed. A child born today possesses approximately the same biological brain as a child born thousands of years ago. But the world of information surrounding that child is entirely different. Language allows each generation to inherit discoveries it did not make. Writing allows knowledge to cross centuries. Technology allows information to move around the planet almost instantly. Human civilization became powerful not because every human is individually capable of rebuilding it. It became powerful because minds are connected across time. Perhaps that connection is the rare threshold. Not intelligence alone, not hands alone, not fire alone, but the creation of a collective memory that continues expanding beyond any individual life. Could a dinosaur lineage have crossed that threshold? Could an aquatic animal have found another route? Could a forgotten mammal have built a culture erased by later ages? There is no evidence that any did. But the biological ingredients existed separately. The planet experimented with vision, grasping, communication, memory, and social learning again and again. Only once, in the known record, did those ingredients combine into an industrial species. Whether that combination was inevitable or almost impossible remains unknown. If the asteroid had missed Earth 66 million years ago, dinosaurs might have continued evolving. Perhaps no technological species would ever appear. Perhaps mammals would have remained small. Perhaps a bird-like lineage would eventually develop greater manipulation and cumulative culture. Or perhaps intelligence would follow a path no human imagination could predict. There is no experiment that can replay the history. Earth happened only once. Every species alive today stands at the end of an unrepeatable chain of events. This makes our existence feel both ordinary and extraordinary. Ordinary, because every feature of the human body emerged through natural processes. Extraordinary, because those processes passed through countless fragile moments. A different climate, a different mutation, a different extinction, a different migration. Any one of them might have prevented technological humanity from appearing. The first civilization on Earth may not have been guaranteed. It may have been a narrow possibility waiting inside billions of years. And perhaps this is why no older civilization has been found. Not because Earth erased it, not because its ruins remain hidden beneath mountains, but because no previous species ever crossed the final distance. Many approached intelligence from different directions. None reached industry. The planet waited through ages of reptiles, forests, oceans, and ice. It waited while continents collided and separated. It waited while intelligent eyes opened in many forms. Then one primate lineage began placing stones into deliberate shapes. Firelight gathered around social groups. Sounds became complex language. Stories preserved memory. Hands built upon the work of earlier hands. The process accelerated. Stone became metal. Villages became cities. Writing became science. Fire became industry. And for the first known time, a species became capable of altering the entire planet deliberately and accidentally. If this is truly Earth's first civilization, then the silence beneath us is not evidence of successful erasure. It is evidence of rarity. The empty geological layers may represent hundreds of millions of years in which intelligence existed, but industry did not. A world filled with minds, perhaps, but not machines. Still, one question remains. If an earlier civilization had crossed that threshold, what precise fingerprints should we seek? Not its imagined face, not the shape of its body, not a human-like statue buried beside a dinosaur. We would need to search for the materials that intelligence rearranges. Metals removed from their ores, molecules created through manufacturing, energy released from ancient carbon, radioactive isotopes separated and transformed, sediments disturbed across entire regions. A civilization might vanish as a culture, yet remain visible as an unnatural pattern of atoms. And so our journey moves away from imagined beings and toward the smallest surviving clues, from minds that cannot fossilize to chemicals that might. If a civilization disappears, its buildings may fall, its roads may fracture, its machines may corrode, its languages may become silent, but the atoms it rearranged do not simply vanish. They move, they react, they dissolve into water, settle into soil, enter living organisms, and become buried beneath new layers of sediment. Over immense periods of time, the recognizable shapes of technology may disappear while its chemistry remains. This is where the search for a lost civilization becomes both more scientific and more difficult. We must stop looking for a machine. We must begin looking for a pattern. A single unusual element would not be enough. Nature concentrates metals. Volcanoes produce strange compounds. Meteorites deliver rare materials. Microorganisms alter chemistry. The oceans sort particles across enormous distances. Earth is constantly creating anomalies. But an industrial civilization might leave several anomalies at once. Carbon altered globally. Metals concentrated far from their natural sources. Artificial molecules buried within sediments. Radioactive isotopes appearing in unusual proportions. Erosion accelerating across continents. Species moving suddenly between isolated ecosystems. Each clue alone might have a natural explanation. Together, they could form something more difficult to dismiss. A fingerprint is not one line. It is an arrangement. The first part of that fingerprint may be carbon. Carbon moves constantly through the planet. Plants remove carbon dioxide from the air. Animals consume carbon through food. Oceans absorb it. Volcanoes release it. Rock weathering slowly removes it again. Some carbon becomes buried within sediment. Some remains underground for millions of years as coal, oil, and natural gas. This movement is known as the carbon cycle. A technological species can disturb that cycle very quickly. Human civilization extracts ancient carbon from deep underground and releases it into the atmosphere through combustion. Carbon that remained isolated for geological ages returns to the active surface environment within only a few centuries. This affects more than the total amount of carbon dioxide. It also changes the balance between different forms of carbon. Atoms of carbon are not all identical. Most contain 6 protons and 6 neutrons. This form is known as carbon-12. A smaller amount contains an additional neutron and is known as carbon-13. Living organisms tend to favor the lighter form during certain chemical processes. Because fossil fuels formed from ancient life, they contain a relatively high proportion of carbon-12. When large quantities of fossil fuels are burned, the atmosphere receives an unusual pulse of lighter carbon. This change can be measured. It can also be preserved. Marine organisms build shells from substances dissolved in seawater. When those organisms die, some shells sink to the ocean floor. Layer after layer accumulates. Their chemistry becomes a record of the water in which they lived. A sudden shift in carbon isotopes can therefore remain visible long after the atmosphere itself has changed. Lake sediments may preserve a similar signal. Soils can record it. Cave formations may contain it. Even the bodies of organisms can reflect the chemistry of their environment. A civilization using fossil carbon on a global scale could therefore create a boundary detectable across many parts of the world. But carbon alone cannot prove technology. Ancient warming events also produced carbon isotope shifts. Volcanism can release carbon. Methane can escape from natural reservoirs. Organic rich sediments can be heated underground. Changes in ocean circulation can move carbon between different parts of the planet. A lost civilization would need to leave additional clues. The rate of change might help. Industrial emissions can occur rapidly. In geological layers, a rapid disturbance may appear as an abrupt boundary, yet sediment accumulates unevenly. A layer representing 1 year in one location might represent a century elsewhere. Animals disturb the seafloor. Roots mix soil. Currents remove or redeposit material. The original timing becomes blurred. What began as a sudden event can look slower after millions of years. The rock record is not a perfect clock. It is a clock damaged by weather, life, and movement. Still, global patterns matter. If the same carbon disturbance appeared within marine sediments, continental rocks, fossils, and mineral deposits of the same age, researchers could conclude that something altered the entire planet. The question would then become what caused it. Volcanoes, biology, an impact, or intelligence. Another clue might be the movement of metals. Technology depends upon concentration. A piece of copper wire contains atoms that once existed within ore. Those atoms were mined, crushed, heated, purified, shaped, transported, and placed inside a machine or building. The final object represents an arrangement of matter that natural processes would be unlikely to create in that location. Cities contain enormous quantities of concentrated metal: iron, copper, aluminium, zinc, tin, lead, chromium, nickel, silver, gold, rare earth elements. These materials arrive from mines across the planet. Some are present in tiny quantities inside electronic devices. Others form the skeletons of buildings and transportation systems. When civilization disappears, the metals begin to spread outward again. Iron rusts and becomes part of soils. Copper reacts with water and oxygen. Lead enters sediments. Particles from industrial surfaces are carried by wind. Rivers move contaminants toward lakes and seas. Landfills leak dissolved elements into groundwater. Eventually, the manufactured objects lose their shapes, but the metals remain unusually concentrated. A future geologist might find a layer containing combinations rarely seen together in nature. Copper beside synthetic glass, lead beside fragments of fired ceramics, chromium mixed with carbon-rich particles, rare earth elements concentrated within a former urban deposit. The individual objects might be unrecognizable. The association would be the clue. Natural sediments often reflect the geology of nearby landscapes. A river carries minerals from the rocks it crosses. A beach contains materials sorted by waves. A volcanic ash layer contains elements produced by a particular magma. An industrial layer can combine substances from distant continents. A tiny device assembled in one city may contain metals mined from several countries. When billions of such objects are produced, the surface of the planet develops chemical mixtures with no simple local origin. This geographical rearrangement may be one of civilization's strongest signatures. A lost species might have transported matter across oceans long before its buildings disappeared. Even if its cities were erased, the planet could remember that movement. Mining itself would create another pattern. Civilization does not remove rock randomly. It follows veins of ore. It extracts layers of coal. It drills into reservoirs of oil and gas. It searches for particular minerals and leaves surrounding material behind. After millions of years, an ancient mine might collapse. Tunnels would fill with water and sediment. Open pits would erode into valleys or lakes. The shapes could become difficult to recognize, but the resource deposit would remain strangely incomplete. A mineral body might appear to have been removed selectively. Useful material could be missing, while less valuable rock remained. Nature can also redistribute ore. Groundwater dissolves minerals. Heat moves metals through cracks. Erosion removes exposed deposits. Tectonic forces break and shift rock. To identify ancient extraction, scientists would need repeated geometric or chemical patterns inconsistent with ordinary geology. Parallel shafts, regularly spaced voids, rock crushed and redeposited in unnatural layers, a trail connecting the depleted deposit with distant concentrations of the same metal. Such evidence would be extraordinary. No confirmed ancient mining system has been discovered from a pre-human civilization, but the thought experiment reveals what a search might require. Not one empty mineral deposit, a network of consequences. Plastics present a different kind of clue. They are among the most visible symbols of modern industry. Lightweight, durable, and easily shaped, plastics enter packaging, construction, clothing, electronics, vehicles, medicine, and almost every part of daily life. They also spread rapidly. Fragments have traveled into rivers, oceans, soils, ice, and living organisms. Tiny particles can settle into marine sediment far from any city. If humanity vanished, plastics would not remain unchanged forever. Sunlight weakens many of them. Heat breaks molecular bonds. Mechanical forces fragment them. Microorganisms can slowly attack certain materials. Burial exposes them to pressure and chemical reactions. Over millions of years, most familiar plastic objects would lose their original form. A future researcher would probably not uncover a perfectly preserved bottle labeled in a human language. Instead, the bottle might become a dark film, a cluster of altered carbon compounds, a microscopic particle trapped between grains of sand, a strange hydrocarbon within sedimentary rock. The challenge would be identifying the artificial structure after it had been transformed. Some plastics might leave more durable traces than others. Additives could remain. Pigments might create unusual mineral combinations. Chlorinated compounds could produce distinctive chemical residues. Layers rich in synthetic polymers might change during burial in ways unlike ordinary plant or animal matter. But deep time is a powerful chemist. Pressure and heat simplify complex molecules. They remove the very organization that made a substance artificial. A plastic's final geological form might resemble natural organic material. This creates an important problem. Technology may survive chemically while losing its technological appearance. To recognize ancient plastics, scientists would need to understand their afterlife. They would study how different polymers react when buried, how they change at increasing temperatures, what minerals form around them, which molecular fragments remain stable, what isotope patterns they create. Perhaps the future search for ancient industry will depend upon laboratory simulations lasting only months, but reproducing conditions that act for millions of years. Researchers could place artificial materials under heat and pressure, then examine what survives. They could build a library of possible technofossils. A technofossil is an object or material created by technological activity that enters the geological record. The word can refer to recognizable artifacts. A piece of concrete, a ceramic fragment, a metal alloy, a particle of plastic. But after enough time, a technofossil may no longer resemble an object. It could become a chemical anomaly, whose original form is impossible to reconstruct. The idea changes our understanding of fossils. Ordinary fossils preserve traces of life. a bone, a shell, a leaf, a footprint, a burrow. Technofossils preserve traces of organized behavior. They represent matter transformed through planning. A naturally broken stone may reveal only erosion. A deliberately shaped stone reveals intention. A natural mineral deposit reveals chemistry. A refined alloy reveals extraction, purification, temperature control, and design. The difficulty is that intention is easiest to recognize, while the arrangement remains intact. A metal blade is obvious. A corroded layer of iron and carbon is less so. Deep time gradually converts evidence of intention into evidence of chemistry. Some artificial materials might resist this process. Ceramics are created when clay or other minerals are heated to high temperatures. The heating permanently changes their structure. Fired clay can survive burial for very long periods. Human archaeologists recover pottery because it resists ordinary decay. An industrial civilization could produce vast quantities of ceramic material. Tiles, bricks, pipes, insulators, laboratory equipment, protective coatings, parts designed to survive extreme heat. After millions of years, complete objects might be rare, but fragments could remain. Their mineral structures might reveal temperatures or manufacturing processes not normally reached within surface environments. Repeated shapes could provide additional evidence. A single smooth fragment might be natural. Thousands of fragments with identical thickness and composition would be harder to explain. Glass may preserve similar clues. Nature produces glass through volcanic eruptions, lightning strikes, and meteorite impacts. Artificial glass, therefore, cannot be identified simply because it is glass. But manufactured compositions can differ from natural examples. Additives alter color, strength, melting temperature, and optical properties. Layers of glass mixed with metal, ceramic, and synthetic compounds could suggest construction or industry. If an ancient glass object were melted again by volcanism or impact, its original shape would vanish. Its chemical composition might still remain slightly unusual. Again, context would matter more than the object alone. Concrete could become one of humanity's most widespread technofossils. It is already produced in enormous quantities. Concrete combines cement, water, sand, stone, and often steel reinforcement. When structures collapse, the material breaks into fragments. Rivers may carry those fragments. Waves may smooth them. Sediment may bury them. Over time, pieces of concrete can become incorporated into new sedimentary rock. The artificial stone becomes part of natural stone. A future cliff might contain rounded fragments of roads, buildings, and bridges. The fragments would no longer stand as architecture. They would appear as pebbles. But their internal mixture could reveal manufacturing. Natural rock forms through geological processes. Concrete is assembled according to recipes. Its grains, pores, chemical bonds, and additives may form repeated patterns. A layer containing countless fragments could mark the location of a destroyed urban region. Yet even concrete eventually changes. Groundwater moves through it. Minerals dissolve and recrystallize. Heat alters its structure. After tens or hundreds of millions of years, some fragments might be difficult to distinguish from natural sedimentary rocks. The older the civilization, the more its materials would need to be read through subtle differences. Radioactive elements may leave longer-lived clues. Nuclear technology deliberately changes the nuclei of atoms. It separates isotopes. It produces new elements. It creates ratios that may be rare outside reactors or explosions. Some radioactive isotopes decay in seconds. Others survive for years, thousands of years, or much longer. After millions of years, many direct products would no longer remain. But radioactive decay does not erase matter. It transforms one element into another. The final stable products may appear in unusual proportions. Imagine a buried nuclear waste site. Containers corrode. Groundwater enters. Radioactive materials move slowly through surrounding rock. Over time, the original facility disappears. But mineral grains in the region record radiation damage. Daughter products accumulate. Isotope ratios remain abnormal. A future geologist might recognize that nuclear reactions occurred there. Would that prove technology? Not immediately. Nature has produced nuclear fission on Earth without civilization. The natural reactors once active in ancient uranium deposits demonstrate that unusual nuclear chemistry can emerge when the correct physical conditions align. A technological interpretation would require evidence of control. Materials concentrated beyond natural levels. Geometric arrangements. Multiple reactor sites. Artificial barriers. waste products separated from fuel, isotopes distributed through the atmosphere in a pattern resembling explosions. Once again, no single clue is enough. Technology reveals itself through relationships. A nuclear civilization might also leave a signal in global sediment. Atmospheric detonations spread particles widely. Some settle into soil and the ocean. If the isotopes survive long enough, they form a time marker connecting distant locations. Humanity has already created such markers. Future geologists could identify a boundary associated with the nuclear age even after most structures disappeared. A lost civilization using similar energy might create a comparable horizon. But suppose it used no nuclear technology. Suppose it relied on sunlight, wind, tides, geothermal heat, or biological systems. Its carbon signature might be much weaker. A sustainable civilization could be much harder to detect than an unstable one. This possibility complicates the entire hypothesis. We tend to imagine industrial civilization through our own history. Coal smoke, oil wells, metal factories, plastic production, nuclear reactors, rapid environmental change. But technology does not require the same path. Another species might develop high levels of knowledge without burning fossil fuels extensively. It could build with biodegradable materials. It could recycle metals efficiently. Its population might remain small. Its energy use might be distributed rather than concentrated. Such a civilization could survive for a long time while leaving only a faint geological signal. Paradoxically, the most environmentally careful civilization might be the easiest for deep time to erase. A destructive civilization writes loudly into stone. A balanced one may whisper. This also affects the search for intelligence beyond Earth. Astronomers sometimes discuss technosignatures. These are signs of technology detectable across interstellar distances. Radio transmissions are one example. Artificial light on a planet's night side could be another. Certain atmospheric pollutants might reveal industry. Large structures could alter the light from a star. Waste heat might betray extensive energy use. But all of these ideas assume that technology creates visible inefficiency. Energy escapes. Chemicals accumulate. Signals spread. A mature civilization might avoid such waste. It could become quieter as it becomes more advanced. Its technology might merge with natural cycles. Instead of covering a planet with factories, it might design biological systems to perform manufacturing. Instead of releasing pollutants, it might reuse every material. Instead of broadcasting powerful radio signals, it might communicate through narrow and efficient beams. Its world could appear natural from a distance. Perhaps civilization is easiest to detect during a brief and unstable adolescence, a period when energy use grows faster than wisdom, when waste accumulates, when the atmosphere changes, when technology remains powerful but poorly integrated with the planet supporting it. If so, the geological record may preserve only short windows of technological visibility. Humanity may be living inside one of those windows now. A future species searching for us would detect not our intelligence directly, but our inefficiency, the carbon we failed to contain, the metals we scattered, the plastics we abandoned, the species we transported, the radioactive particles we released. Our greatest geological monument may be waste. This thought is unsettling because civilizations usually celebrate what they build: palaces, libraries, observatories, bridges, works of art. But geology may preserve something else. A landfill more clearly than a poem, a pollution layer more clearly than a philosophy, a change in extinction rates more clearly than a scientific discovery. The record does not judge value, it records material persistence. A ceramic toilet may outlast a digital archive. A plastic fragment may survive longer than a symphony. A trace of lead pollution may remain when every name in history has vanished. What we consider meaningful and what geology preserves are very different. A lost civilization might therefore be represented by the least noble parts of its existence: its waste, its emissions, its mining scars, its chemical accidents. Perhaps researchers would never know its achievements. They might see only the damage surrounding them. A thin layer of environmental disturbance would become the entire surviving biography of a species. This is another reason caution is necessary. An unusual layer might show that something happened. It would not reveal why. A civilization could release carbon accidentally or deliberately. It might collapse from environmental change or survive and move elsewhere. It might use certain metals for machines or for art. Its synthetic compounds might support medicine, communication, or war. Chemistry preserves consequence, not intention. Even if evidence of ancient industry were discovered, the inner story would remain inaccessible. We could estimate its energy use, its duration, perhaps its geographical spread. But we might never know what its inhabitants believed, whether they understood the damage they caused, whether they looked toward the future, whether they tried to preserve their world. The most personal parts would be the first to vanish. There may be another type of signature hidden within minerals, known as stable isotopes. Oxygen, nitrogen, sulfur, and other elements also exist in different isotopic forms. Industry affects their cycles. Fertilizers change nitrogen patterns. Fossil fuel combustion alters sulfur deposits. Mining and manufacturing move materials between reservoirs. A civilization could create simultaneous isotope shifts across several elements. This combined pattern might be more distinctive than carbon alone. Imagine a sediment layer in which carbon becomes lighter. Nitrogen changes due to large-scale fertilizer production. Sulfur reflects combustion. Metals appear in concentrated quantities. Erosion increases. Synthetic molecules emerge. Species become globally mixed. The more independent signals align, the less likely coincidence becomes. Scientists sometimes refer to this kind of reasoning as multiple lines of evidence. A single observation may be uncertain. Several observations supporting the same explanation can become persuasive. This is how a lost civilization would need to be discovered. Not through one sensational object, through a network of quiet measurements. A core drilled from the seafloor, a mineral layer inside a cave, a chemical pattern within fossil shells, a concentration of rare elements in an ancient lake bed, a microscopic fragment that resists natural explanation. One clue would lead to another. The event would appear at the same moment in distant locations. Natural explanations would be tested and gradually eliminated. Only then could the possibility of technology be considered seriously. No such combined signal has been confirmed. The known geological record remains consistent with natural planetary history until humanity's rise. But the methods developed through this thought experiment are still valuable. They help scientists understand the Anthropocene, the proposed interval in which human activity has become a major influence on Earth's systems. They help predict what parts of modern civilization may survive. They guide the search for techno-signatures on other worlds, and they teach humility about preservation. We are surrounded by objects that feel permanent because they will outlive us. A bridge may last longer than its engineer. A monument may survive many governments. A glass bottle may remain after everyone who touched it is gone. But geological time measures permanence differently. Millions of years are not simply many human lifetimes placed end to end. They are enough time for continents to move, for oceans to open, for mountains to rise and erode, for buried sediment to become stone, for stone to melt and begin again. Within that process, almost every object becomes temporary. Yet chemical patterns can survive astonishing journeys. A grain may be buried beneath kilometers of sediment. It may experience pressure and heat. It may rise again within a mountain. Rain may free it. A river may carry it to a new sea. It may be buried a second time. Matter travels. A trace left by civilization could survive not because it remained undisturbed, but because some part of its unusual composition endured every transformation. The message would not remain where it was written. It would be carried through the planet. Perhaps future researchers would find only scattered pieces, a strange metal ratio in one continent, an artificial molecular fragment in another, a carbon boundary beneath an ancient ocean. The locations would seem unrelated until dating revealed that they belonged to the same moment. Then a lost global event would slowly emerge. This is how deep history is often reconstructed. No single rock contains the entire story. Scientists compare fragments from many places. One location preserves the atmosphere, another preserves the ocean, another preserves life on land, another preserves volcanic activity. Together they form a world. If an earlier civilization existed, its discovery would likely happen the same way. It would not rise from the ground as a complete city. It would be assembled intellectually from incomplete evidence. A civilization reconstructed from atoms. There is something almost poetic in that possibility. Technology begins by arranging matter into meaningful forms. Tools, homes, symbols, machines. After the builders disappear, Earth slowly removes the arrangement. Meaning dissolves. Matter remains. Millions of years later, another intelligence might reverse the process. It would begin with the matter and attempt to recover the lost meaning. A pattern of isotopes becomes evidence of energy use. A metal concentration becomes evidence of extraction. A synthetic residue becomes evidence of manufacturing. A global extinction pattern becomes evidence of planetary influence. From chemistry, the researchers would imagine behavior. From behavior, they would imagine minds. The lost civilization would be rebuilt first, not in stone, but in thought. Still, every reconstruction would contain uncertainty. Perhaps the unusual metals came from volcanism. Perhaps the carbon pulse came from methane. Perhaps the molecular fragment entered the sample through contamination. Perhaps the isotope pattern was changed by groundwater. The older the evidence, the more pathways exist for confusion. Science would need to move slowly. The discovery, if it ever came, would not begin with certainty. It would begin with a question. Why are these atoms here? Why do they appear at the same time? Why does the pattern repeat across the planet? Why does no known natural process explain all of it? Only after years of study might the answer become difficult to avoid. Something organized matter. Something extracted energy. Something changed the world. Until such evidence is found, the Silurian hypothesis remains what it was designed to be. A disciplined thought experiment. A way of asking what civilization means geologically. A reminder that technology becomes visible through its environmental consequences. And a mirror held before our own age. We often imagine the future remembering us through our greatest creations. Perhaps it will. Perhaps some archive will survive. Perhaps a spacecraft drifting beyond the solar system will preserve human designs long after Earth changes. But within the rocks, the record will be different. A carbon pulse, a scattering of plastics, a layer of metals, a burst of radioactivity, a sudden movement of species. This may be the language in which our civilization introduces itself to deep time. No voice, no face, only chemistry. And if another civilization once spoke through that same language, its message may already surround us. Inside cliffs, beneath oceans, within minerals collected and stored in quiet laboratories. Not obvious enough to declare itself, not clear enough to become history. Only a faint and patient arrangement of atoms, waiting for someone to recognize that nature may not have placed them there alone. If a civilization existed millions of years before humanity, finding its remains would depend as much upon location as upon technology. Some environments destroy evidence quickly, others protect it. A machine abandoned in a tropical forest would face moisture, roots, microorganisms, and constant chemical activity. A similar object sealed inside dry salt might remain recognizable for far longer. A city built along an active coastline could be scattered by waves and later carried into a tectonic trench. A small settlement buried rapidly beneath volcanic ash might survive in remarkable detail. Preservation is uneven. Earth does not decide which moments are important. It preserves whatever happens to enter the right conditions. This is why paleontologists do not search everywhere equally. They look for rocks formed in environments where remains were buried quickly and later escaped destruction. Ancient lake beds, river floodplains, fine marine sediments, volcanic ash deposits, caves, tar seeps, dry deserts, frozen ground. Each environment keeps a different kind of memory. If traces of an earlier civilization existed, they would probably be hidden within the same geological archives that preserve ancient life. But the best place to search for bones may not be the best place to search for technology. A skeleton and a chemical pollution signal follow different paths. A building and an isotope disturbance require different conditions. Scientists would need to search many forms of evidence at once. The deep ocean may contain one of the most complete records of planetary change. Far below the waves, tiny particles settle continuously through the water. Dust carried from continents, ash from volcanic eruptions, shells from microscopic organisms, organic matter from the sunlit surface, minerals formed through chemical reactions. The particles gather slowly upon the seafloor. In some regions, only a few millimeters accumulate over thousands of years. Layer by layer, the sediment becomes an archive. A research ship can lower a drilling system through the water and recover a long cylinder of mud and rock. This cylinder is known as a core. The youngest sediment lies near the top. Older material rests below. By studying the chemistry, fossils, and magnetic properties of each layer, Researchers can reconstruct ancient environments. A core may reveal when temperatures changed, when volcanic ash reached the ocean, when dust increased during dry periods, when marine organisms appeared or disappeared, when the ocean became acidic or lost oxygen. If an industrial civilization altered the entire atmosphere, its signal could enter these marine sediments. Carbon released into the air would exchange with the ocean. Pollutants carried by wind and rivers would settle into mud. Metal particles could travel far from their source. Changes in climate would alter the species living near the surface. Their shells would preserve the new conditions. The civilization's cities might vanish, yet the ocean could retain a distant chemical echo. Deep marine sediment has several advantages. It can record global changes. It accumulates over long periods. Some seafloor regions remain relatively undisturbed, but the archive is not permanent. Oceanic crust eventually moves towards subduction zones. There it descends beneath another tectonic plate. Sediment may be scraped away and added to the edge of a continent, or it may be carried downward, heated, deformed, and destroyed. Most modern ocean floor is geologically young. The farther back researchers travel, the less original seafloor remains. Evidence from hundreds of millions of years ago must often be found where ancient marine sediments were lifted onto continents. Rocks exposed in mountains, deserts, and cliffs may once have rested beneath vanished seas. A person walking across dry land can stand upon an ancient ocean floor without realizing it. Layers of limestone may contain the remains of microscopic marine organisms. Dark shale may record oxygen-poor water. Ripples preserved in stone may reveal currents that moved before the first humans existed. A civilization's global chemical signature could survive in such rocks, even when the ocean that received it had disappeared. But locating the correct layer would be difficult. Earth contains enormous volumes of sedimentary rock. Only a small portion is exposed at the surface. Some layers lie kilometers underground. Others were removed by erosion. Still others were altered by heat and pressure until their original chemistry became difficult to interpret. Scientists would need to know approximately when to search. Without a suspected time interval, the task would be almost impossibly broad. One strategy would be to begin with known moments of rapid change: carbon disturbances, mass extinctions, sudden metal enrichments, unusual sediment layers. Researchers could re-examine these boundaries for signals not explained by natural processes. This does not mean assuming that every catastrophe was industrial. It means using existing anomalies as starting points. The geological record is already filled with boundaries that attract scientific attention. Some mark impacts, some mark volcanic events, some mark evolutionary transitions. If an artificial signal existed, it might first be noticed because it did not fit comfortably within the established explanation. Yet searching only known catastrophes creates a bias. A sustainable civilization might not produce a dramatic extinction or carbon pulse. It could leave a faint layer during an otherwise ordinary interval. Researchers focused only on crises might miss it completely. The most detectable civilization would not necessarily be the most advanced. It might simply be the most disruptive. Lake sediments offer another valuable archive. Lakes receive material from the surrounding landscape. Rivers carry soil, pollen, ash, and chemical compounds into them. Particles settle to the bottom, sometimes forming thin annual layers. In quiet lakes, summer and winter can produce slightly different sediments. The resulting pairs are called varves. Like tree rings, they can record the passing of years. A lake near an ancient urban or industrial region might preserve local evidence with extraordinary detail. Metal pollution, charcoal from widespread burning, changes in vegetation caused by agriculture, synthetic compounds, sudden erosion from roads, mines, or cleared land, bones and shells from introduced species. A deep lake with low oxygen near its bottom could protect delicate material from scavengers and decay. If a civilization collapsed and sediment buried its remains quickly, a lake basin might become a sealed archive. But lakes are temporary in geological terms. They fill with sediment. Rivers change course. Glaciers erase basins. Tectonic forces raise or lower the land. A lake surviving for several million years is unusual. Ancient lake deposits can remain as rock, but only fragments may be preserved. A local industrial signal could easily disappear if the entire basin were eroded. Still, lake sediments might offer the best chance of discovering a civilization that never became global. A small society could leave no worldwide carbon disturbance, but the lake beside its settlements might preserve repeated patterns of activity. Layers of soot, unnatural metals, sudden vegetation changes, perhaps even fragments of manufactured material. The evidence would be local, fragile, and extremely easy to miss. Caves provide a different kind of protection. Inside a cave, objects are sheltered from sunlight, wind, and some forms of erosion. Temperatures may remain relatively stable. Sediment can accumulate slowly. Bones, tools, footprints, pigments, and traces of fire can survive far longer than they would on an exposed surface. Human archaeology depends heavily upon caves because they preserve moments that open landscapes lose. If an earlier intelligent species used caves, perhaps evidence of its behavior could remain. Scratches made deliberately into stone. Repeated hearth-like deposits. Objects carried from distant locations. Bones broken in systematic ways. Pigments applied to walls. Structures built from rock. Yet a cave is not automatically safe for millions of years. Water dissolves limestone. Passages collapse. Minerals grow across surfaces. Floods rearrange sediments. Animals dig. Earthquakes open fractures. A cave may disappear as erosion removes the hillside surrounding it. Still, protected underground spaces offer one of the better environments for preserving direct artifacts. Imagine a simple object placed deep inside a dry cave. A stone tool. A fired ceramic fragment. A metal object wrapped in mineral deposits. If the cave remained stable, the object could survive long after every surface settlement vanished. The problem is scale. Earth contains countless caves, many buried or inaccessible. Only a tiny fraction has been explored scientifically. A lost artifact could remain sealed behind rock with no surface indication that the chamber exists. The object might be preserved perfectly and still be practically undiscoverable. Salt deposits may offer even stronger protection. Salt can form when enclosed bodies of water evaporate. Thick layers accumulate and are later buried beneath sediment. Under pressure, salt behaves slowly like a soft solid. It can move, fold, and rise through surrounding rock. Dry salt environments can preserve organic material by limiting water and microbial activity. For technological material, salt could act as a seal. A chamber buried inside a stable salt formation might remain isolated from groundwater for long periods. This is one reason salt formations are considered for storing hazardous materials. If an earlier civilization placed objects underground intentionally, salt could provide one of the best chances for long-term survival. But there is no evidence that such repositories exist. The idea mainly reveals an interesting possibility. A civilization aware of geological time might try to preserve a message deliberately. Rather than trusting monuments at the surface, it could bury durable objects within stable formations. Ceramic tablets, metal alloys, synthetic crystals, mathematical patterns, instructions for decoding language. A designed archive might survive much longer than an ordinary city. Would humanity recognize it? Perhaps. Repeated geometric shapes would attract attention. Materials arranged in layers could appear artificial, but deep burial would make discovery unlikely. Unless the archive created a detectable signal, future researchers might drill only a few kilometers away and never know it was there. Preservation and discoverability are not the same. The safest hiding place may also be the hardest place to find. Amber is famous for preserving delicate life. It begins as sticky resin produced by trees. Small insects, plant fragments, feathers, and air bubbles can become trapped inside. The resin hardens and changes chemically over time. Under favorable conditions, it becomes amber. Specimens can preserve structures too fragile to survive in ordinary rock. Could amber preserve a technological fragment, a fiber, a microscopic particle, a trace of pigment? A tiny manufactured object could theoretically become trapped in resin. But amber deposits are limited. They preserve small objects, not cities. And the object would need to exist in a forest containing resin-producing trees, then enter the resin, become buried, survive geological change, and eventually be discovered. The sequence would be extraordinarily unlikely, yet a single convincing object could change everything. A microscopic component sealed inside ancient amber would be difficult to explain if it displayed unmistakable manufacturing. Regular circuitry, an alloy unknown in nature, repeated microscopic patterns. No such object has been found. But amber illustrates how tiny pieces of evidence can survive when enormous structures do not. Ice can preserve entire landscapes. In frozen environments, decay slows. Bodies, food, wooden objects, microorganisms, and atmospheric gases can remain trapped for thousands of years. Ice cores drilled from Greenland and Antarctica contain bubbles of ancient air. These bubbles allow scientists to measure past concentrations of carbon dioxide, methane, and other gases. Layers of dust, ash, sea salt, and pollutants reveal changes through time. Human industrial activity already appears within ice. Lead pollution from ancient mining, soot from combustion, radioactive material from nuclear testing, chemical changes associated with modern emissions. An earlier civilization living within the age preserved by current ice sheets might leave a clear record. But ice is not a secure archive across deep time. Glaciers flow. Lower layers deform. Ice melts during warm periods. Antarctica may preserve ice older than 1 million years, and researchers continue searching for exceptionally ancient sequences. Yet this remains very recent compared with dinosaur history. Ice from tens of millions of years ago has vanished. A civilization older than the current polar ice sheets would not be found through intact atmospheric bubbles. Its signal would need to survive elsewhere. Permafrost faces similar limits. Frozen soils can preserve remains beautifully. But climates change. Regions now frozen were once warm. Regions now warm may freeze in the future. Over millions of years, repeated thawing and freezing disturb the record. Glaciers are excellent historians of recent climate and poor librarians of deep planetary time. Deserts may preserve some materials through dryness. In environments with little rainfall, wood, fabric, skin, and pigments can survive far longer than they would in humid regions. Human artifacts thousands of years old remain recognizable within desert caves and tombs. A lost civilization in an ancient dry region might leave unusually complete remains. But deserts move. Climate belts shift as continents drift and mountain ranges rise. A landscape that remained dry for 10,000 years may become wet over 1 million. Rivers may cut through it. Sand dunes migrate. Wind abrades exposed surfaces. The same dryness that slows decay can expose objects to erosion. Eventually, geological change overwhelms the protection. Volcanic ash can preserve moments almost instantly. A powerful eruption may bury forests, settlements, animals, and landscapes beneath thick material. Fine ash enters spaces and covers surfaces. When burial is rapid, objects can be protected from weather and scavengers. Human history provides famous examples of towns preserved by eruptions. In deep time, volcanic deposits have also captured footprints, leaves, and entire ecosystems. If an earlier civilization lived near an active volcano, an eruption might preserve buildings or artifacts beneath ash. This may be one of the few situations in which recognizable structures could survive for millions of years. The buried site would then need to avoid later destruction. It could not be melted by new magma. It could not be eroded away. It would need to remain within accessible rock. Even then, scientists might interpret the structures cautiously. Natural fractures can form straight lines. Cooling lava can create columns. Minerals can produce geometric patterns. A convincing city would require repeated walls, internal spaces, manufactured materials, and relationships inconsistent with geology. No such pre-human site has been confirmed. Still, volcanic burial reminds us that direct preservation is not impossible. It is merely rare. Perhaps the most unusual archive lies beyond Earth. The moon has no rivers, no oceans, no forests, no weather in the familiar sense. It has no active plate tectonics recycling its crust. Its surface changes mainly through impacts, radiation, and the slow movement of dust. Objects placed there can remain for extremely long periods, although they are gradually damaged by micrometeorites, temperature extremes, and solar radiation. Human missions have already left equipment, footprints, landing stages, scientific instruments, and other material on the moon. On Earth, many comparable objects will eventually disappear. On the moon, some may remain recognizable far longer. This creates a remarkable idea. If an earlier terrestrial civilization developed space travel, the best evidence of its existence might not be on Earth at all. It might be on the moon, a probe, a lander, a buried component, a structure placed within a sheltered lava tube. Even a crash site could preserve unusual alloys and manufactured fragments. The moon's surface is ancient. Some regions have remained relatively stable for billions of years. A technological object there might survive long after Earth erased its builders. But this possibility requires the hypothetical civilization to have reached space. That is a major assumption. A society could become industrial without developing rockets. It might collapse quickly. Its biology might make spaceflight difficult. Its culture might lack interest in leaving the planet. Nevertheless, lunar archaeology offers an interesting extension of the Silurian question. Searching Earth alone may not be enough. The Moon has recorded impacts from asteroids and comets throughout solar system history. It may also contain pieces of Earth blasted into space by ancient collisions. When a large object strikes Earth, fragments of crust can escape the planet. Some may eventually land on the Moon. Those fragments could preserve material from periods poorly represented on Earth. Ancient minerals, chemical signatures, perhaps microscopic fossils. In theory, pieces of Earth's old surface may rest within lunar soil, protected from the tectonic recycling that destroyed their original source. Finding them would be extraordinarily difficult. They would be mixed among vast quantities of lunar material. Identifying their origin would require careful chemical analysis. But the Moon may contain pages from Earth's history that Earth itself has lost. If an ancient industrial layer was struck by a large impact, tiny pieces could have been launched outward. A fragment containing unusual material might survive on the Moon. This is speculative. There is no known evidence of such a deposit. Yet it demonstrates how evidence can migrate beyond the world that created it. Mars could provide another external archive. Fragments of Earth have reached Mars naturally, and Martian meteorites have reached Earth. The planets exchange small amounts of material through impacts. An advanced civilization might also send spacecraft there. Mars has erosion, dust radiation, ancient volcanism, and some geological activity, but it lacks Earth's global ocean and active plate recycling. Objects on or beneath its surface might persist for very long periods. If an earlier Earth civilization explored Mars, its equipment could survive better than its cities at home. Again, the idea depends upon a technological level for which no evidence exists. But it raises a broader principle. Civilizations may be preserved best at the edges of their reach. The central world remains geologically alive. Its surface is recycled. Its atmosphere and oceans erase structures. Quiet destinations preserve what the home planet destroys. Asteroids may provide even more stable locations. A probe placed on a small airless body could remain for immense periods. A spacecraft traveling beyond the planets might survive longer still. Humanity has already sent several objects onto paths that may carry them through interstellar space. Their surfaces will be damaged. Their systems will stop operating. Their structures may be altered by radiation and impacts. But some could remain as artificial objects long after Earth becomes unrecognizable. A civilization may disappear locally, while its debris continues traveling through the galaxy. This suggests an unsettling possibility. The oldest evidence of technological life may not be found on a living planet. It may drift between stars. A silent machine whose builders vanished millions of years earlier. The object might pass through another planetary system. It might become captured by gravity. It could fall onto a moon or asteroid. Future beings might discover it without ever finding the world from which it came. The artifact would be separated from its context. Its makers would exist only as an inference. Yet searching the vastness of space for such objects is enormously difficult. Interstellar distances are overwhelming. A small artificial body could pass through a solar system unnoticed. Even within our own solar system, countless asteroids remain poorly studied. A manufactured object millions of years old might resemble an ordinary dark rock from a distance. Only close examination would reveal regular internal structures or unusual material composition. The sky is a larger archaeological site than Earth, but it is also far harder to excavate. Back on our planet, drilling may provide access to evidence unavailable at the surface. Oil, gas, mineral, and scientific boreholes bring up rock from kilometers below. These samples reveal ancient environments hidden beneath younger layers. A civilization buried deeply might first be detected accidentally. An unexpected metal concentration, a thin layer containing altered polymers, a cavity with unusual geometry, a fragment of fired material within sediment far older than humanity. Such a discovery would need to be treated carefully. Modern drilling introduces contamination. Metal from the drill bit enters samples. Lubricants contain industrial compounds. Plastic equipment can shed particles. The deeper and more extraordinary the claim, the more important it becomes to exclude material introduced during collection. Independent samples from several locations would be necessary. The signal would need to appear consistently within sealed ancient rock. Dating would need to confirm that the material truly belonged to the surrounding layer. Extraordinary evidence can be created accidentally by ordinary tools. This is one reason ancient technosignature research would require specially designed methods. Scientists might use equipment made from materials absent from the signal being sought. They could collect duplicate cores. They might preserve untouched control samples. Several laboratories would test the material independently. Every stage would need documentation. The discovery of a possible artificial compound would be only the beginning. Researchers would ask whether microorganisms could produce it, whether heat and pressure could form it naturally, whether it entered through groundwater, whether it was introduced during drilling, transport, storage, or analysis. A convincing result would survive all of these tests. The search may also depend upon museums and existing collections. Geologists have gathered rocks for centuries. Cores from oceans, lakes, glaciers, and drilling projects are stored in archives around the world. Fossils and mineral samples fill museum drawers. Some were collected before scientists knew which chemical signals to examine. Evidence of an unusual event could already exist within these collections. A future analytical technique might reveal patterns invisible today. This happens often in science. A specimen is collected for one purpose. Decades later, new technology allows researchers to ask different questions. Microscopes improve, dating becomes more precise, chemical instruments detect smaller quantities. Imaging reveals internal structures without destroying the sample. Old rocks gain new information. A possible ancient technosignature might not require a new expedition. It might require a new way of reading something already found. Yet this creates another difficulty. When researchers search through enormous datasets, unusual patterns inevitably appear by chance. A single strange measurement can look significant. Confirmation requires repetition. The anomaly must be found again. It must occur within geological context. Its distribution must make sense. The more samples examined, the more false positives will appear. Patience protects the search from imagination. Perhaps no lost civilization exists to be found. In that case, the work would still improve our understanding of Earth. Researchers would learn how synthetic materials decay, how industrial signals enter sediments, which environments preserve pollution, how long human influence may remain detectable. This knowledge helps future societies make decisions about waste, nuclear storage, and environmental restoration. The search for a previous civilization becomes a study of our own afterlife. Where should humanity place a message intended to survive? A stone monument at the surface may erode. A digital archive may lose power. A satellite may fall. A cave may collapse. A lunar vault might last, but only if future beings reach it. A message can survive physically and still fail because no one knows it exists. True long-term communication requires durability, discoverability, and interpretation. The message must remain, it must be found, and it must be understood. Mathematics is often proposed as a universal language. Simple sequences, geometric relationships, astronomical diagrams, patterns of prime numbers. These could reveal intention even when spoken language is lost. A durable archive might repeat the same information through several media. Carved stone, ceramic, metal, microscopic patterns, genetic encoding, objects placed in multiple environments. The more copies distributed, the greater the chance that one survives. Perhaps an earlier civilization, aware of its vulnerability, would have done the same. If so, we might search for repetition, identical objects in distant geological settings, the same mathematical pattern carved into materials from different continents, artificial markers placed at regular intervals. A single strange object can be disputed. A designed network is harder to explain naturally. No such network has been discovered. Earth's ancient rocks remain silent, but silence has several meanings. Nothing may have been written. The message may have been destroyed. It may remain buried, or we may not yet understand how to read it. Science cannot treat all possibilities as equally likely. The absence of evidence across extensive geological study strongly supports the conclusion that humanity is Earth's first industrial civilization. Researchers have examined ancient sediments in extraordinary detail. They have found impacts, extinctions, volcanic crises, climate transitions, and biological revolutions. None requires technology. If a previous civilization had become global and heavily industrial, some combined signature would probably have attracted attention. Yet the chance of finding a small, brief, or low-impact society would be much lower. The hypothesis survives mainly within that narrow space. Not an empire covering the planet for millions of years. That would almost certainly leave extensive evidence. But perhaps a civilization lasting a few centuries, limited to one region, using materials that decayed easily, never reaching space, destroyed before its influence became global. Such a society could be hidden more effectively. Its existence would still be unsupported, but geological preservation alone could not rule it out with perfect certainty. Perfect certainty is rare when studying deep time. Scientists work with probabilities. The fossil record makes some histories strongly supported and others extremely unlikely. It does not preserve every event. This uncertainty should not become an excuse for believing anything. It should become motivation for precise questions. What environment would preserve the evidence? What material would survive? What natural process could imitate it? How could contamination be excluded? What additional clue should appear if the interpretation were correct? A scientific mystery becomes useful when it produces testable expectations. The Silurian Hypothesis does not ask us merely to imagine ruins. It asks us to predict where traces would be found and what they would look like. In ocean sediments, perhaps a global chemical disturbance. In lake deposits, local pollution and erosion. In caves, durable artifacts or repeated markings. In salt, sealed manufactured materials. In volcanic ash, a landscape buried suddenly. On the moon, objects beyond Earth's geological recycling. Within stored samples, patterns waiting for instruments not yet developed. The search moves across scales, from entire planets to microscopic grains, from mountain ranges to isotope ratios, from abandoned cities to a single artificial crystal. A civilization could be enormous in experience and almost invisible in preservation. All its lives, conflicts, discoveries, and dreams might narrow into one unusual layer, one drill core, one fragment, one pattern that should not be there. For now, no such pattern has crossed the boundary from speculation into evidence. The rocks tell a story of natural change followed, very recently, by humanity. But the places capable of keeping older secrets still exist. Sediments continue settling in darkness beneath the ocean. Minerals continue growing within caves. Salt formations remain sealed underground. The moon keeps its airless surface beneath the stars. Museums hold drawers that may not be opened for decades. The archive of Earth is incomplete, damaged and scattered, yet it is not empty. Every surviving layer contains something the planet managed not to erase. A climate, an ocean, a forest, an extinction, a footprint, a grain of ash, and perhaps, somewhere in that immense collection of imperfect memories, there remains a trace whose meaning has not yet been recognized. Not a city waiting beneath the soil, not a sleeping machine, only a small interruption in the ordinary language of nature. A material moved where nature would not move it. A shape repeated too precisely. A chemical combination appearing across distant places at the same moment. A whisper preserved in stone. The question is whether anyone was there to make it, or whether Earth, through its endless creativity, once again created the appearance of intention without a mind behind it. The Silurian Hypothesis begins beneath our feet. It asks whether Earth could have hosted an industrial civilization so long ago that geology erased almost every direct trace. But once the question is asked here, it naturally expands outward. Earth is not the only ancient world. Mars has existed for roughly the same length of time. Venus formed from similar materials. Countless planets beyond the solar system may have had oceans, atmospheres, continents, and stable climates long before human beings appeared. If civilizations can rise and disappear, then the universe may contain worlds that were inhabited in the past but appear lifeless today. The silence of a planet may not mean that nothing ever happened there. It may mean that the story ended before anyone arrived to listen. This changes the search for extraterrestrial intelligence. We usually imagine alien civilizations as living societies. Somewhere, at this moment, machines operate beneath another sun. Cities glow through the night. Radio signals cross space. Spacecraft move between planets. A telescope points toward Earth. But civilizations may be temporary. Stars survive for billions of years. planets remain long after cultures collapse. The technological phase of a species might last only centuries, millennia, or tens of thousands of years. Even a civilization enduring for 1 million years would occupy only a narrow fraction of a planet's history. Two technological societies could exist within the same galaxy and never overlap in time. One might vanish before the other evolves. The distance between them would not be measured only in light years. It would also be measured in ages. This creates a form of cosmic archaeology. Instead of searching only for living intelligence, we might search for the remains of intelligence, dead probes, abandoned structures, artificial atmospheric chemistry, unusual planetary surfaces, mining scars, waste heat from machines still operating without builders, or chemical disturbances preserved after an industrial society disappeared. The search becomes wider, but also more difficult. A living civilization may transmit information intentionally. A vanished civilization cannot explain what it left behind. Its evidence must survive distance, time, and interpretation. Astronomers receive only light from most distant worlds. Within that light, they must search for patterns, an atmosphere out of balance, a surface reflecting unusual materials, a planet whose day side and night side release heat in unexpected ways, a star dimmed by objects that do not resemble ordinary planets or dust. These signals are called technosignatures when they may indicate technology. But as on Earth, nature can imitate many of them. A strange atmosphere may result from industry or volcanism. An unusual reflection may come from artificial materials, or ice, clouds, salt, or minerals. A sudden dimming of a star may be caused by large structures or by dust passing through the system. The lesson of the Silurian Hypothesis follows us into space. A mysterious pattern is not evidence of civilization until natural explanations have been examined carefully. Still, the possibility remains. A civilization could disappear while its planet carried the consequences. Imagine a world orbiting a distant star. For billions of years, it contains oceans. Its climate is stable enough for life to develop. Single-celled organisms appear. Complex life follows. Eventually, one species becomes capable of cumulative culture. It learns to control energy. It builds cities. It extracts resources. For several centuries, its technology expands rapidly. Its atmosphere changes. Artificial compounds spread through the oceans. Satellites fill the sky. Then something happens. Perhaps the civilization collapses. Perhaps it moves away. Perhaps it transforms into a form we would no longer recognize. Perhaps its population declines gradually until its machines fall silent. Millions of years later, the planet remains. Forests may cover the ruins. Oceans may bury coastal cities. Plate tectonics may recycle the surface. The atmosphere may return toward equilibrium. To a distant telescope, the world could appear natural. Any observers arriving late would see only a quiet planet. Perhaps a few unusual chemical traces remain. Perhaps an orbiting object continues circling overhead. Perhaps nothing obvious survives. The civilization existed, yet the universe appears empty. This is one possible explanation for the Great Silence. The galaxy may not lack intelligence. It may lack synchronized intelligence. Civilizations could be scattered across time, like brief lights flashing during different nights. Humanity sees the stars only during its own moment. The ancient lights have already gone dark. The future ones have not yet appeared. Mars is the nearest world where this question feels almost tangible. Today, Mars is cold, dry, and exposed. Its atmosphere is thin. Liquid water is unstable across most of the surface. Dust moves through empty landscapes. Volcanoes stand silent. Canyons stretch across distances larger than countries. No confirmed evidence shows that life ever existed there. Yet ancient Mars was different. Its surface contains dried river channels. Valleys show the movement of water. Minerals formed in wet environments. Some regions may once have contained lakes. A northern ocean has been proposed, although its full history remains uncertain. Long ago, Mars possessed a thicker atmosphere and a more active climate. For some period, parts of the planet may have offered conditions suitable for microbial life. Whether those conditions lasted long enough for complex organisms is unknown. Whether life began there at all is unknown, and there is no evidence of a Martian civilization. Still, Mars provides a natural laboratory for thinking about planetary memory. Unlike Earth, Mars has no active system of plate tectonics recycling its entire surface. Much of its crust is ancient. Some landscapes have remained recognizable for billions of years. A river delta formed in the distant past can still be studied today. Impact craters remain visible. Layers of sediment preserve changing environments. If an early technological species somehow emerged on Mars, certain traces might survive better than comparable evidence on Earth. Roads would be covered by dust, but perhaps not consumed by forests. Metal objects would face radiation, oxidation, and temperature changes, yet they might remain as altered fragments. Buried structures could persist beneath dry sediment. Mining pits might remain visible from orbit. The lack of rain and plate recycling could protect large-scale features, but Mars is not perfectly preservative. Its atmosphere carries dust. Wind erodes rock. Impacts disturb the surface. Radiation breaks chemical bonds. Temperature changes fracture materials. Ancient water altered minerals. Buried ice moves and disappears. Volcanism has resurfaced parts of the planet. Over billions of years, even Mars can erase. A civilization from the planet's warmer youth would be extraordinarily ancient. Its remains would need to survive not millions, but perhaps billions of years. At that depth of time, direct objects would be difficult to preserve anywhere. Yet the Martian surface is vast and only lightly explored. Human spacecraft have examined a tiny number of locations. Orbiters can map large features, but small objects disappear within the landscape. A ruined structure several meters across could resemble fractured rock. A buried deposit could remain invisible. Even on Earth, where millions of people explore, drill, mine, and build, archaeological discoveries continue. On Mars, most places have never been examined closely. This does not make an ancient Martian civilization likely. No known evidence points toward one, but it reminds us how little direct inspection has occurred. If scientists search for ancient Martian life, they may also need to remain open to unusual signs of organization, repeated geometric structures, materials concentrated unnaturally, isotope patterns suggesting artificial processing. Yet extraordinary caution would be required. Mars is filled with shapes that appear familiar. Hills resemble faces. Rocks resemble bones. Shadows create straight lines. Cracks form polygons. Human perception searches for meaning inside randomness. From a distance, natural features can look engineered. This tendency is known as pareidolia. It turns clouds into animals and mountain shadows into buildings. On another planet, where every landscape feels unfamiliar, the effect becomes stronger. A convincing technosignature would need more than resemblance. A possible wall would need consistent material composition. A geometric feature would need internal organization. A suspected road would need connect locations in meaningful ways. A manufactured object would need repeated structures nature does not ordinarily produce. The difference between curiosity and evidence is measurement. If Mars once supported only microbial life, even that discovery would transform our understanding of biology. It would suggest that life can begin more than once within a single planetary system. If Earth and Mars developed life independently, the universe might be biologically fertile. But if Martian life shared ancestry with Earth life, perhaps material traveled between the planets through impacts. The two biospheres could represent one origin spreading between worlds. Either result would be profound. Civilization is a much larger step. Before discussing lost Martian cities, scientists must first determine whether life ever existed there at all. Still, the concept of planetary archaeology may influence future missions. Rovers already examine rocks for signs of water and ancient habitability. More advanced missions could search for complex chemical patterns. Drilling beneath the radiation-damaged surface might reveal preserved organic material. Samples returned to Earth could be studied with instruments too large to send to Mars. If an artificial compound existed, its discovery would need to survive the strictest possible testing. Contamination from Earth would be an immediate concern. Spacecraft carry materials made by human industry: lubricants, plastics, metals, sterilizing chemicals, microscopic particles. A future sample containing something synthetic might record our own visit rather than ancient Martian technology. The search for alien technosignatures therefore begins with controlling human fingerprints. We must avoid becoming the evidence we hope to discover. Venus presents a different mystery. In size and overall composition, Venus resembles Earth more closely than Mars does. Its gravity is similar. It is built from rocky material. It formed within the same young solar system. Yet the surface of Venus today is extraordinarily hostile. Its atmosphere is dominated by carbon dioxide. Clouds containing sulfuric acid surround the planet. Pressure at the surface is crushing. Temperatures are hot enough to damage many familiar metals and electronics. A world sometimes described as Earth's sister has become almost completely alien. But Venus may not always have been this way. Some climate models suggest that ancient Venus could once have supported milder conditions, possibly including liquid water, although the duration and extent of any habitable period remain uncertain. Its early history is difficult to reconstruct. The planet's surface is relatively young in geological terms. Large regions were reshaped by volcanism. The atmosphere and heat make exploration difficult. Only a small number of landers have survived briefly on the ground. If Venus once contained oceans and a temperate climate, could life have emerged there? Could complex life have appeared? Could a civilization have risen before the planet entered its present greenhouse state? There is no evidence that this happened. Yet Venus may be a stronger example of planetary erasure than Mars. A civilization living there billions or hundreds of millions of years ago could have faced a world transformed beyond recognition. Its oceans would disappear. Its surface would be heated intensely. Volcanism could bury or destroy structures. Chemical reactions would alter almost every exposed material. The thick atmosphere would hide the ground from ordinary telescopes. Even future explorers might find the original surface record heavily damaged. If an industrial civilization contributed to a runaway climate transition, its final impact might become almost impossible to separate from natural planetary evolution. The entire world would appear as the catastrophe. There might be no surviving boundary between civilization and collapse, only the final atmosphere. This creates a chilling version of the Silurian question: could a planet's present uninhabitability be the last techno-signature of a civilization? Perhaps a society releases greenhouse gases until oceans evaporate. Water vapor strengthens the warming. Ultraviolet light breaks water molecules high in the atmosphere. Hydrogen escapes to space. The planet loses its oceans and becomes permanently altered. Long after buildings disappear, the atmosphere remains. But natural processes can also produce runaway greenhouse conditions. Distance from the star, volcanic gases, cloud behavior, and planetary rotation all matter. A hot carbon-rich atmosphere does not indicate industrial collapse by itself. The same ambiguity returns. Nature and technology may create similar outcomes. Without preserved artificial compounds, unusual isotope patterns, or direct artifacts, a dead world cannot tell us why it died. Venus also demonstrates that habitability is not permanent. A planet may spend only part of its life within conditions suitable for complex organisms. We often search for worlds inside a star's habitable zone, where liquid water could exist. But the habitable zone changes. Stars brighten as they age. Atmospheres evolve. Continents alter climate. Oceans are lost or frozen. A world could be habitable for 1 billion years and sterile for the next 3 billion. Observing it today would reveal only the final state. The galaxy may contain many former Earths, planets where rain once fell. Rivers moved, life spread, perhaps minds emerged. Then the conditions changed. From far away, those worlds would appear as ordinary deserts, frozen spheres, or cloud-covered furnaces. Their living eras would survive only in buried geology. This is why searching for life requires studying planetary history rather than only present conditions. Mars is dry now, but ancient rivers matter. Venus is hot now, but its earlier climate matters. Icy moons appear frozen, but oceans may exist beneath their surfaces. A planet's current appearance is one frame from a long film. Civilization could occupy only a few moments within that film. The moons of the outer solar system expand the mystery further. Europa, one of Jupiter's large moons, contains strong evidence for a global ocean beneath an icy shell. Enceladus, orbiting Saturn, releases plumes of water and other material from fractures near its south pole. Titan possesses a thick atmosphere, lakes of liquid hydrocarbons, and complex organic chemistry. These worlds are not Earth-like on the surface, but they may contain environments where unusual forms of life could exist. If intelligent life evolved within a subsurface ocean, its civilization would face conditions radically different from ours. It might never see the stars. Kilometers of ice could separate it from space. Fire would be unavailable underwater. Metallurgy would be difficult. Communication across the ocean might use sound, chemistry, electric fields, or light produced biologically. Technology could develop through controlled organisms, mineral structures, or geothermal energy. Its cities might be grown rather than built. Its machines might be living systems. Its information might be encoded within molecules. Would such a civilization leave technofossils we could recognize? Perhaps not. A biologically engineered structure might decompose like an ordinary organism. A chemical network could leave no metal tools. Artificial ecosystems might resemble natural evolution after the builders vanished. Our search methods are shaped by terrestrial industry. We look for pollution, radio signals, artificial light, and manufactured materials. A civilization beneath ice might produce none of these. Its ocean could contain intelligence for millions of years, while the moon appeared quiet from outside. It would be hidden not by distance alone, but by environment. This possibility broadens the meaning of cosmic silence. Perhaps the universe contains minds that never become astronomers. A species beneath a sealed ocean may not know that planets or stars exist. Its concept of the universe could end at the ice ceiling. It might develop science, history, art, and technology without discovering the sky. If it vanished, no signal would ever leave the moon. The civilization would exist entirely within one hidden ocean and disappear there. The stars would remain unaware. Humanity's ability to observe the cosmos depends upon living beneath a transparent atmosphere. We see sunlight, we see the moon, we see planets and stars. Their regular movements inspired calendars, navigation, mathematics, and ideas about physical law. An intelligent species beneath thick clouds might see less. A species underground might see nothing. Astronomy is not guaranteed by intelligence. Neither is space travel. The universe may contain civilizations confined by their environments long before technology has a chance to free them. Exoplanets make the question almost limitless. Thousands of worlds have been confirmed beyond the solar system, and many more almost certainly wait to be found. Some are giant planets orbiting close to their stars. Others are rocky. Some circle red dwarfs. Some belong to systems with several planets packed into small regions. Their diversity exceeds the simple categories imagined before their discovery. Among them may be planets that were once habitable but are no longer. A world close to an aging star could have lost its oceans. A planet around an active red dwarf might have had its atmosphere stripped away. A large impact could have transformed another. A global glaciation could have frozen the surface. A civilization may have existed before these events. From Earth, direct archaeological evidence would be almost impossible to detect. At interstellar distances, even planets are tiny points hidden within the light of their stars. Astronomers usually cannot see continents, much less ruins. They study planetary size, mass, orbit, temperature, and atmosphere. A lost civilization would need to leave a signal on a planetary scale. Atmospheric pollutants could provide one possibility. Certain manufactured gases are rare in nature and can remain in an atmosphere for long periods. If telescopes detected them in large quantities, especially alongside other signs of industry, technology might be considered. But a vanished civilization's pollutants would eventually break down. Ultraviolet radiation destroys molecules. Chemical reactions remove them. Oceans absorb gases. Rocks weather. The atmosphere cleans itself at different rates depending on the compound. Some technosignatures may remain visible for centuries, others for thousands or millions of years. Most would not last for the age of a planet. Observing a chemical civilization requires arriving during or soon after its technological phase. Again, timing becomes crucial. Artificial structures in orbit might last longer. A civilization could surround its planet with satellites, habitats, mirrors, or energy collectors. After the society collapsed, some objects might remain in stable orbits. Collisions would create debris. Atmospheric drag would remove lower objects. Radiation and impacts would degrade materials. Orbital resonances could preserve others. A thick and unusual debris field might survive for a time. From far away, astronomers could possibly detect irregular changes in starlight as large objects passed in front of the star. But natural rings, moons, comets, and dust can produce similar signals. Only a pattern showing clear organization would be persuasive. Repeated geometric occultations, regular structures changing in coordinated ways, spectral evidence of manufactured material. Even then, natural explanations would be tested first. A more advanced civilization might build on scales large enough to alter the energy of an entire star system. It could collect a significant portion of its star's light. Rather than one solid sphere, it might use an enormous swarm of orbiting structures. Such a system would absorb visible light and release energy as heat. Astronomers have proposed searching for unusual infrared emissions that might reveal this waste heat. If the builders vanished, parts of the swarm might continue orbiting. The structure could become a fossil civilization visible across great distances. But it would not remain orderly forever. Objects would collide, orbits would shift, maintenance systems would fail. Some structures would fall into the star or escape the system. Unless automated repair continued, the technological arrangement would slowly become debris. The civilization's monument would decay into an unusual dust cloud. At what point would technology become indistinguishable from nature? Perhaps after enough time, observers would see only warm dust around an ordinary star. They might interpret it as the remains of planetary collisions. The true history would be lost. This is the cosmic version of a city becoming sediment. Order becomes disorder. Machinery becomes material. Intention becomes chemistry and heat. A spacecraft traveling between stars could remain recognizable much longer. Interstellar space is thin. There is no rain, wind, or biological decay. A probe could drift for millions or billions of years. Radiation would damage electronics. Microscopic dust impacts would erode surfaces. Extreme temperature cycles might fracture components. But the overall structure could survive, especially if designed for durability. Humanity has already launched spacecraft that will continue moving through the galaxy after they stop functioning. They are small, slow, and unlikely to approach another inhabited world. Yet they demonstrate that technological objects can outlive civilizations and planets. An ancient alien probe could exist within our solar system. It might orbit the sun, rest on an asteroid, lie buried on the moon, drift through the distant region beyond Neptune. Perhaps it entered millions of years ago and became inactive. This idea is speculative. No confirmed alien artifact has been discovered. The solar system is also vast. A small object could remain unnoticed. Human surveys are improving, but many distant and dark bodies are difficult to observe. An artificial probe designed to remain hidden would be harder still. A probe not designed to communicate might appear as an ordinary object until examined closely. The question becomes archaeological rather than communicative. Instead of waiting for a message, we would search for something left behind, a material that should not occur naturally. A hollow asteroid, an object with an unusual orbit, a surface showing manufactured geometry, an internal heat source inconsistent with its size. But every anomaly must be approached carefully. Unusual orbits can arise naturally. Asteroids contain cavities and strange shapes. Radioactivity produces heat. Collisions create flat surfaces and sharp edges. Nature works across billions of years and enormous numbers of objects. Rare natural events are expected somewhere. The larger the search, the more strange examples we will find. Evidence of technology must exceed strangeness. It must show organization. There is another possibility. A civilization may intentionally leave durable markers for future species. Perhaps it knows that it will disappear. Perhaps it wishes to communicate across deep time. Where should it place the message? A planet with active geology is unreliable. An atmosphere changes. Oceans erase coastlines. Continents recycle. An airless moon may be better. A stable asteroid could preserve an object. A probe placed at a gravitationally balanced point might remain detectable. An artificial beacon could activate only when another spacecraft approaches. A message could be encoded within the spectrum of a long-lived laser, or within the structure of a biological organism engineered to survive. An advanced society might understand preservation far better than we do. It could construct materials resistant to radiation and impacts. It might distribute many copies across its system. It could arrange objects into unmistakable mathematical patterns. The absence of such markers nearby might suggest that no earlier technological visitor chose to leave them, or that they remain undiscovered, or that their design is beyond our recognition. A message may be obvious, only to a mind sharing the assumptions of its maker. Humans often imagine prime numbers as universal, but another intelligence might not represent number visually. We imagine diagrams of atoms, planets, and DNA. Another species may experience the world primarily through sound, smell, electric fields, or pressure. Even mathematics needs a physical code. The sender chooses marks, intervals, shapes, or frequencies. The receiver must recognize that the variation carries meaning. An ancient alien archive could be mistaken for natural complexity, or a natural crystal could be mistaken for a message. Communication across species is difficult even when both are alive. Communication across millions of years is harder. The builders cannot correct misunderstanding. They cannot answer questions. Their message becomes an artifact surrounded by silence. Perhaps the most durable message is not a sentence, but impossibility. A structure so unlikely to arise naturally that any observer must infer design. Perfectly nested chambers. A sequence of isotopes arranged according to mathematical rules. A manufactured object placed where geology cannot explain it. A map encoded through multiple independent methods. Redundancy would matter. The same idea repeated through shape, chemistry, rhythm, and number. Even if one code failed, another might survive. If humanity ever creates such an archive, it would become an attempt to speak beyond the lifespan of our species, not to people in the next century, to minds existing after our continents have moved. They might be human descendants, another terrestrial species, or visitors from elsewhere. The archive would say only that someone was here. Perhaps that is the deepest message any civilization can leave. Not its entire history, not every name or achievement, only the proof of awareness, matter arranged by a mind. The Silurian Hypothesis makes this desire understandable. If Earth can erase civilization, then deliberate memory becomes an act of resistance against geology. We build archives because we know forgetting is possible. We create monuments because lives are brief. We send spacecraft outward because planets are temporary. A civilization's reach into space may be part exploration and part preservation. Every object leaving Earth carries something of our existence beyond the systems that can erase us here. But even space is not eternal. Stars evolve, orbits change, galaxies collide, radiation damages matter, black holes consume. Protons themselves may not last forever, although their ultimate stability remains unknown. There is no perfect archive, only longer forms of survival. This realization gives cosmic archaeology a quiet sadness. We search for civilizations that may have tried to be remembered. Their messages could already be damaged. Their worlds could be gone. Their stars may have changed. We may detect only fragments. A burst of radio waves crossing space long after its transmitters failed. A machine continuing its programmed path without understanding. An atmosphere carrying the final pollution of an extinct society. A planet whose surface was altered, but whose builders have become unrecognizable dust. The universe may be full of aftermaths. We are accustomed to looking for life as a present-tense phenomenon. Is anything alive there now? Is anyone transmitting now? But astronomy is always a study of the past. Light requires time to travel. When we observe the moon, we see it as it was a little more than 1 second earlier. The sun appears as it was several minutes ago. Nearby stars appear years in the past. Distant galaxies appear millions or billions of years ago. A signal from an alien civilization might reach Earth after that civilization no longer exists. Every telescope is a time machine, but it cannot choose the time it sees. Distance decides. Suppose a civilization 1,000 light-years away transmitted a message 1,000 years ago. We would receive it today. If we replied immediately, our response would arrive 1,000 years from now. The original senders might be gone. Their language may have changed. Their species may have transformed. Communication across interstellar space can resemble archaeology, even when the participants are alive. Each message belongs to an earlier version of the sender. At larger distances, the delay becomes more severe. A galaxy observed 10 million light-years away appears as it was 10 million years ago. Any civilization visible there may already have vanished. A civilization existing there today will not be visible to us for another 10 million years. The cosmic present cannot be observed as one shared moment. Every region arrives through a different past. This makes the question, are we alone, more complicated than it seems. Alone where? Alone now. Alone during the interval visible to our telescopes. A civilization may exist beyond the reach of its current light. Another may be visible, even though it has already ended. The universe can appear inhabited by ghosts and empty of neighbors at the same time. A technosignature is therefore not necessarily an invitation. It may be a fossil made of light. Consider a distant planet whose atmosphere contains artificial compounds. The photons carrying that information began their journey years or centuries ago. By the time astronomers analyze them, the source may have changed. The pollution could have disappeared. The civilization could have recovered or collapsed. We would be studying a historical event without knowing its outcome. The planet would become a remote geological layer, not in stone, but in a spectrum. Lines of color revealing gases that existed at one moment beneath another star. Perhaps future telescopes will identify a world with oxygen, water vapor, and methane. These gases may suggest biology. Then an additional compound appears, something difficult to produce naturally. Researchers examine every alternative: photochemistry, volcanism, instrumental error, contamination. The signal remains. More observations confirm it. A technological origin becomes plausible. The discovery would be historic. Yet we would still know almost nothing. Is the civilization active? Did it create the compound intentionally? Is the planet healthy or damaged? Are its inhabitants aware of other stars? How long ago did the observed light leave? The technosignature would reveal existence without experience. It would be like finding one chemical layer from an ancient Earth civilization, a fingerprint without a face. Perhaps this is all cosmic archaeology can offer at first, a pattern requiring intelligence, then years of patient interpretation. The search may also discover worlds where a civilization seems to have disappeared. Imagine repeated observations showing artificial pollutants declining, night-side illumination fading, orbital structures breaking apart, an atmosphere moving toward a new equilibrium. Scientists might witness the aftermath of collapse across decades, or perhaps the changes would have natural explanations: clouds shifting, volcanic activity ending, a ring system dispersing. The interpretation would remain uncertain. We should be careful not to project human fears onto every distant anomaly. A changing planet is not necessarily a dying civilization, but studying possible collapse could help us recognize the temporal nature of technosignatures. Civilizations may not shine steadily, they may flicker. A short burst of radio transmission, a century of industrial pollution, a few thousand years of visible megastructures. Then silence. Search strategies based on continuous signals could miss them. Astronomers may need to examine historical observations for changes. Old photographic plates, archived radio data, repeated atmospheric spectra. A signal detected once and dismissed might have been brief. A technosignature can disappear before instruments improve enough to confirm it. Cosmic archaeology therefore depends upon archives of our own. Every observation preserves the sky as it appeared at one moment. Future scientists may compare centuries of data: a star that once dimmed strangely, a planet whose atmosphere changed, a radio source that transmitted for only a few years. The evidence of another civilization might exist not in the future sky, but in measurements already recorded. The universe changes slowly at human scales, but technology can change quickly. An alien industrial phase may begin and end between two generations of telescopes. Preserving data becomes a way of preserving other worlds. The Silurian Hypothesis also asks us to reconsider extinction. On Earth, a species disappears from the fossil record. Its biological lineage ends. But a technological species could leave descendants that are not biological: machines, artificial organisms, self-repairing probes, digital minds. If the original builders vanished, their technology might continue. Would the civilization be extinct? Perhaps biologically, perhaps not culturally. A machine carrying its knowledge could act as a surviving branch. It might maintain archives, explore planets, and reproduce new machines. The civilization's bodies would be gone, but its organized information would continue. In this case, cosmic archaeology could encounter active artifacts from an extinct species. A probe may follow instructions created millions of years earlier. It may not be conscious, or it may contain a form of awareness descended from its makers. The distinction between ruin and survivor becomes unclear. A self-maintaining machine could outlast the world that built it. Its power source might eventually fail. Its memory could decay. But before that, It might travel across enormous distances. If such machines exist, they could be among the most detectable remains of past civilizations. They would not require the original society to remain stable for millions of years. Only the machines would need endurance. Some may search, some may observe, some may wait. Again, there is no evidence that such alien probes have been found, but the idea follows naturally from the difference between biological and technological survival. Life depends upon environments. Machines can be designed for environments their builders cannot tolerate. A species living on one planet might send its technology into regions where its biology could never survive. Its civilization becomes distributed. If the homeworld dies, fragments continue elsewhere. Humanity has begun this process in a very small way. Our spacecraft operate on planets, moons, asteroids, and in deep space. They carry cameras, instruments, messages, and engineering choices. Most will fail quickly by cosmic standards. Yet they are the earliest pieces of human activity no longer confined to Earth. If our species vanished, those objects would briefly become our external fossil record. The closest evidence of humanity might eventually be found on the Moon or Mars rather than here. This possibility returns us to Earth with a different perspective. Perhaps looking for earlier terrestrial civilization should include the solar system. If a pre-human technological species reached space, its most durable remains might be beyond our atmosphere. But if no such remains are found, the simplest conclusion remains that there was no earlier spacefaring species. The absence of lunar cities or ancient probes does not prove this absolutely. The search is incomplete, yet a widespread technological civilization capable of exploring space would be expected to leave more than one fragile trace. The larger its reach, the harder complete erasure becomes. This principle applies across the universe. A small civilization can vanish quietly. A planetary civilization leaves stronger marks. A star-spanning civilization should leave many. If extremely advanced societies were common and long-lived, the galaxy might contain abundant visible engineering. The fact that no confirmed evidence has been observed suggests several possibilities. Advanced civilizations may be rare. They may be short-lived. They may avoid large-scale visible engineering. They may use technologies we cannot recognize. Or they may exist at distances and times that prevent detection. The silence does not choose between these explanations. It only tells us that obvious evidence has not yet appeared. The Silurian Hypothesis encourages a humble response. We should neither declare the universe empty, nor fill every mystery with aliens. We should improve the search, understand natural planetary changes, model how artificial signals decay, learn which materials survive, examine atmospheres over time, search nearby airless bodies for unusual objects, preserve astronomical data, develop instruments capable of distinguishing chemistry created by life, geology, and technology. The work may find nothing artificial. Even then, it will reveal how planets evolve. It will teach us how atmospheres recover or collapse, how long pollutants remain, how surfaces preserve ancient events, how civilizations could become visible to distant observers, and how quickly they could disappear. Perhaps one day, a telescope will examine a nearby rocky planet. The world will not look alive. Its atmosphere may be thin, its surface may be dry, yet the spectrum will contain something unexpected, a compound requiring repeated manufacturing, an isotope ratio that does not match known geology, a reflective layer spread across part of the surface. No radio signal will answer, no lights will glow. The planet will remain silent. Scientists may debate for years. Natural explanations will be tested. Additional observations will be made. Slowly, one conclusion may become difficult to avoid. Someone lived there, not now, long ago. The discovery would answer one question and open countless others. What were they? How long did they exist? What happened? Did they know their world was changing? Did they leave intentionally? Did any descendants escape? Are their artifacts still moving through space? The planet would become the first known archaeological site beyond Earth. Yet no human hand could touch it. Its ruins would exist only as patterns of light. Perhaps the greatest distance would not be the space between our worlds. It would be the time between our civilizations. We would know that intelligence appeared twice in the universe, but we might never exchange a single thought. There is a quiet loneliness in that possibility. to discover that we were never alone, only too late. The stars could hold many such worlds, planets that once carried oceans and voices, moons where hidden societies lived beneath ice, systems filled with machines whose creators disappeared, signals still traveling after their transmitters fell silent. The universe may not be empty, it may be ancient beyond communication. Every civilization could arrive in the ruins of others, separated by geological ages. Some may find artifacts, most may find only unusual chemistry, some may never realize that intelligence preceded them. A planet could build its second civilization above the buried remains of its first. Its inhabitants might ask the same question we do. Are we the first? They might study their rocks, search their moons, analyze their atmosphere, and perhaps, beneath an ordinary layer of ancient sediment, they might find a pattern too organized to be natural, a trace from beings whose names cannot be recovered. The discovery would change their place in history. They would no longer see intelligence as a single miracle beginning with them. They would become inheritors of a world shaped by forgotten minds. Humanity may never make such a discovery. The evidence may not exist. Earth's record points toward us as its first industrial species. Mars and Venus provide no confirmed sign of earlier civilizations. No alien artifact has been verified within the solar system. No distant technosignature has yet crossed the boundary from possibility into proof. For now, the universe remains silent. But silence is not always emptiness. A room can be silent after everyone leaves. A city can be silent beneath sediment. A planet can be silent after its atmosphere changes. A star system can be silent while dead machines continue orbiting. We hear only the present signals reaching us. We do not hear every history. The question, "Where is everyone?" may have a melancholy answer. They were here, somewhere, at another time. Their worlds remembered them briefly. Then weather, geology, radiation, and orbital motion continued. The structures failed, the chemicals dispersed, the signals weakened, the light traveled outward until no detector remained close enough to notice. And yet complete disappearance may be almost impossible. A fragment may remain on an airless moon, a probe may drift between stars, a strange molecule may persist in ancient rock. A planet's atmosphere may carry one final imbalance. A telescope on a young world may collect the photons and wonder why the pattern seems deliberate. Across the darkness, one civilization could discover another without ever meeting it. Not through conversation, through archaeology, through the patient reconstruction of a vanished intelligence from matter, chemistry, and light. Perhaps that will be humanity's first encounter. Not a spacecraft descending through our clouds, not a message announcing a living neighbor, only evidence that, somewhere beneath a distant sun, a civilization once existed. A civilization that rose, looked outward, and disappeared, leaving behind the same question we hope to answer about Earth. How much of a world can a civilization change before the world changes enough to erase it? The possibility of a lost civilization begins as a question about the past. Could another intelligent species have risen before humanity? Could it have transformed the planet, exhausted its resources, and disappeared? Could Earth have erased almost every trace? But slowly, the question turns around. It stops asking only what may have happened millions of years ago. It begins asking what is happening now. Human civilization is young. Its industrial phase has lasted only a few centuries. Its ability to alter the entire planet is younger still. For most of human existence, our ancestors lived in small communities. They gathered plants. They hunted animals. They used fire. They shaped stone, wood, bone, and fiber. Their influence could be powerful locally, but the atmosphere and oceans remained beyond their control. Then the scale changed. Agriculture spread. Forests were cleared. Cities expanded. Metals were extracted. Coal, oil, and natural gas released energy, stored over geological ages. Machines multiplied human strength. Transport connected continents. Information began moving almost instantly. A species that once depended upon the rhythm of one landscape became a force operating across the whole Earth. This transition occurred with astonishing speed. In geological terms, industrial civilization did not rise gradually. It appeared almost as a sudden event. A future geologist studying our time might see no clear distinction between the invention of the steam engine, the arrival of electrical grids, the spread of automobiles, and the beginning of digital technology. These events feel separated to us. They belong to different generations. To deep time, they may collapse into the same narrow layer, a thin boundary where one species abruptly changed the chemistry of its world. This raises an uncomfortable possibility. Perhaps technological civilizations often become visible only shortly before they become unstable. The moment a species gains the power to transform a planet may also be the moment it gains the power to damage the systems supporting it. Energy gives freedom. It also increases consequence. A small population using simple tools can make mistakes without affecting an entire world. A global civilization cannot. Its actions move through the atmosphere. They enter the ocean. They alter climate, soil, forests, and the distribution of life. Its errors become planetary experiments. The species may understand the risks only after the changes have already begun. This idea connects with one of the most famous mysteries in the search for extraterrestrial intelligence: the Fermi paradox. The Milky Way is ancient. It contains enormous numbers of stars. Many of those stars possess planets. Some planets formed billions of years before Earth. If technological civilizations are common and capable of surviving for long periods, then at least some should have had enough time to spread widely through the galaxy. Yet no confirmed signal has been found. No verified spacecraft has arrived. No unmistakable structure has been observed around another star. The galaxy appears quiet. The Fermi paradox is the tension between the apparent possibility of widespread civilizations and the absence of clear evidence. There are many possible explanations. Perhaps life itself is rare. Perhaps complex cells are rare. Perhaps intelligence rarely becomes technological. Perhaps civilizations do exist, but they are too distant. Perhaps they do not use radio for long. Perhaps they avoid contact. Perhaps our instruments remain too limited. Or perhaps technological civilizations tend not to survive. This final possibility is sometimes connected with the idea of the Great Filter. The Great Filter is not one specific event. It is a way of describing any extremely difficult step that prevents most matter from becoming a long-lived, spacefaring civilization. The filter could lie behind us. Perhaps the origin of life is extraordinarily improbable. A planet may have oceans and organic chemistry for billions of years without ever producing the first self-replicating organism. If that step is the filter, then Earth has already passed through something rare. The universe could contain countless habitable planets and almost no life. Or perhaps simple life begins easily, but complex life rarely appears. Earth remained dominated by microorganisms for most of its history. The transition from simple cells to complex cells may have required an unusual sequence of events. If so, microbial worlds could be common, while animals and plants remain rare. The filter might lie at the level of intelligence. Many planets could contain complex ecosystems without producing a species capable of cumulative culture. Evolution rewards survival, not technology. A world may remain biologically rich for billions of years without anything building a radio telescope. The filter could also lie between intelligence and industry. An intelligent marine species might lack fire. A social animal might possess no precise manipulators. A clever species might never invent writing. A culture could become complex without developing scientific institutions or high-energy technology. But the most unsettling possibility is that the filter lies ahead. Perhaps civilizations regularly reach the industrial stage. Perhaps they become visible briefly through pollution, radio waves, artificial light, and planetary change. Then they disappear. They may exhaust essential resources, destabilize their climate, create weapons they cannot control, develop technologies faster than their social systems can adapt, lose the ecological conditions supporting agriculture, fragment into conflict, or become dependent upon networks too complex to repair after disruption. In this view, the silence of the galaxy would not mean that intelligence is rare. It would mean that durability is rare. Civilizations may rise often and vanish quickly. Their technological phases would become brief sparks, separated by enormous distances and long periods of darkness. The Silurian Hypothesis gives this possibility a geological form. If a civilization collapses, how long does its evidence remain obvious? From the perspective of another world, perhaps not long. Radio transmissions weaken as they travel. Artificial gases break down. Satellites fall. Cities erode. The period during which technology can be detected may be much shorter than the period during which a planet appears habitable. A civilization could exist for 10,000 years and remain invisible for the next billion. The galaxy might contain many buried histories and very few active beacons. Humanity cannot yet know whether the Great Filter is real. We have only one example of technological civilization. From a sample of one, no reliable lifespan can be calculated. Perhaps civilizations commonly survive their dangerous early stages. Perhaps they become peaceful, stable, and difficult to detect. Perhaps they spread slowly through space. Perhaps humanity is not approaching an inevitable collapse, but passing through a temporary period of rapid change. The future remains open. Still, the question encourages us to look carefully at the relationship between intelligence and survival. Intelligence allowed humans to adapt to many environments. It allowed us to predict seasons, build shelters, develop medicine, and understand the motion of planets. But intelligence does not guarantee wisdom. A species can recognize a danger without responding to it effectively. Knowledge may be distributed unevenly. People may agree that a problem exists while disagreeing about responsibility, urgency, or solutions. Institutions can move more slowly than technology. Short-term rewards can encourage actions with long-term costs. Civilization is not one mind making one decision. It is billions of individuals, companies, governments, communities, and systems interacting. This complexity creates strength. It also creates delay. No single person controls the global atmosphere. Yet the atmosphere responds to the combined actions of everyone. No one intends to acidify an ocean when starting a vehicle or using electricity. The planetary result emerges from countless ordinary choices. A civilization can alter its world without choosing consciously to do so. This may be one of the dangers shared by technological species. The more energy they use, the larger the gap between individual intention and collective consequence becomes. A factory provides employment and useful products. A power station supplies homes. A farm feeds people. A road connects communities. Each action may serve a clear purpose. Together, across an entire planet, they can transform climate, nutrient cycles, habitats, and biodiversity. The civilization becomes a geological force before it becomes a unified planetary decision-maker. Perhaps this imbalance is temporary. Awareness may eventually catch up with capability. Science reveals the consequences. Technology creates cleaner alternatives. Institutions improve. Cultures develop new values. A civilization learns to measure its influence and remain within the limits of its world. If it succeeds, the dangerous industrial phase may become a transition rather than an ending. This would change its geological signature. Early industry might create a sharp pulse of pollution and carbon. Later stability could reduce the disturbance. The civilization would not disappear. It would become quieter. From far away, its techno-signatures might weaken even as its knowledge increased. This creates another explanation for the cosmic silence. Advanced civilizations may not be loud. Humanity often imagines progress as greater consumption, more energy, more structures, more visible activity. But maturity might involve efficiency. Materials recycled through closed systems, energy gathered without destabilizing climate, cities integrated with ecosystems, technology becoming less wasteful and less externally visible. A successful civilization might resemble nature more closely over time. Its planet would remain healthy. Its atmosphere would no longer contain obvious industrial pollutants. Its machines could become small, distributed, or biological. Its communication might use focused signals rather than uncontrolled broadcasts. The civilization could be present without creating the techno-signatures we expect. If so, our current industrial phase may not represent the normal appearance of advanced intelligence. It may represent its brief adolescence, a noisy period between biological limitation and technological balance. We do not yet know whether humanity will complete that transition. Our geological layer is being written while we are still deciding what kind of civilization we will become. Future rock does not preserve intentions. It preserves outcomes. Plans to reduce emissions do not alter sediment unless they are carried out. Concern for biodiversity leaves no fossil unless extinctions slow. Environmental awareness does not change atmospheric chemistry by itself. The geological record responds only to physical action. This makes deep time an impartial observer. It cannot be persuaded by speeches. It records carbon, temperature, metals, pollen, bones, plastic, sediment. The planet measures civilization through consequence. What is our present consequence? Atmospheric carbon dioxide is increasing. Oceans absorb part of that carbon and become more acidic. Temperatures shift. Glaciers and ice sheets lose mass. Species move toward new regions. Some populations decline. Forests are cleared in some places and restored in others. Rivers are dammed. Nitrogen and phosphorus enter ecosystems in altered quantities. Plastics move through water, soil, air, and living bodies. Mining transfers material from deep rock into cities and waste. Human civilization now affects nearly every major system at Earth's surface. This does not mean humanity is certain to collapse. It means our presence will not be geologically invisible. Even if every city vanished, the planet would remember this interval. The signal may become known as the Anthropocene. The term is used to describe the period during which human activity became a dominant influence upon climate and the environment. Scientists continue debating whether it should be defined formally as a geological epoch, where its boundary should be placed, and which marker best represents it. But beyond formal classification, the physical influence is real. Human activity has created a distinct planetary signal. A future civilization might identify the boundary through several clues. Carbon isotopes would show the rapid burning of fossil fuels. Radioactive particles would mark nuclear testing. Plastic fragments would appear in sediments. Industrial metals would become unusually concentrated. Concrete and aluminium would spread widely. Pollen would reveal changing vegetation. Bones would show the extraordinary abundance of domesticated animals. Species would appear far beyond their original ranges. Many wild populations would decline at the same time. The boundary might look sudden. Before it, ecosystems developed through ordinary biological and geological processes. After it, one organism reorganized the world. A future geologist may not need to find human bones to identify humanity. Chickens might provide a stronger signal. Billions are raised across the planet. Their bones accumulate in large numbers. Their bodies have been shaped through selective breeding. They are transported into regions where their wild ancestors never lived. A layer containing enormous quantities of similar domesticated animals could reveal an agricultural civilization. Cattle and pigs may produce related signals. Crop pollen could show plants spreading beyond natural boundaries. Rats and other species associated with human settlements could appear suddenly across distant environments. Our civilization is embedded within the life it moves. This biological signature may survive longer than many machines. The future record could therefore reveal a strange ecosystem. One primate increases dramatically. A small group of domesticated animals becomes extraordinarily abundant. Wild habitats shrink. Species move between continents. Extinction rates rise. Then perhaps the pattern changes. What happens after that boundary depends upon choices still being made. One possibility is continuation without correction. Energy use increases through methods that destabilize climate. Habitats decline. Food and water systems become stressed. Political conflict grows. Infrastructure is damaged by environmental extremes. Complex networks become more fragile. Eventually, civilization contracts. Population declines. Industrial activity weakens. Emissions fall not because of planning, but because systems fail. The geological signal ends with collapse. This is the dark version of the Great Filter. A civilization gains planetary power, but never develops planetary coordination. Its intelligence solves immediate problems while creating larger ones. It becomes capable of seeing the danger and incapable of changing direction. Another possibility is technological escape. The civilization recognizes the limits of fossil fuels and develops cleaner sources of energy. It redesigns agriculture, restores ecosystems, reduces waste, stabilizes population and consumption, protects water and soil, improves its ability to cooperate across borders and generations. The geological disturbance reaches a peak and then declines. The civilization remains. Its relationship with Earth changes. It becomes not a temporary layer of crisis, but a long-lived participant in planetary systems. This would not require perfection. No civilization avoids all mistakes. Natural disasters continue. Conflicts may occur. Technologies create new risks. But survival does not require a flawless society. It requires the ability to learn before damage becomes irreversible. In this sense, the Great Filter may not be one wall. It may be a series of tests. Can a species control fire without burning its environment beyond recovery? Can it use fossil energy without becoming permanently dependent upon it? Can it develop nuclear physics without destroying itself? Can it create global communication without losing the ability to distinguish truth from noise? Can it build artificial intelligence and biotechnology while maintaining control over how they are used? Can it cooperate at the scale of the consequences it creates? Can it think beyond individual lifetimes? Each technology expands possibility. Each also expands the scale of failure. A civilization survives by developing responsibility at the same speed as power. Perhaps most civilizations fail because these rates are unequal. Technology may advance quickly through competition. Wisdom develops slowly through culture, education, experience, and institutions. A new invention can spread in years. A new ethical framework may require generations. By the time societies understand one technology, another has already changed the conditions. The civilization remains permanently behind itself. It races forward while learning from consequences that arrive later. Climate change demonstrates this delay clearly. Carbon dioxide released today influences the climate for long periods. The full consequence does not appear immediately. Oceans absorb heat slowly. Ice sheets respond over time. Infrastructure built for one climate remains in place as conditions shift. Actions and effects become separated. A species evolved to respond to immediate dangers may struggle with delayed planetary risks. A predator appears now. A storm arrives now. A fire burns now. Climate change unfolds through averages, probabilities, and long-term trends. Its danger is real, but distributed. There may be no single moment when the entire civilization feels the same urgency. This makes response more difficult. An earlier industrial civilization, if one existed, would have faced similar physical laws. Its atmosphere would not care about politics. Its oceans would respond to heat and chemistry. Its resources would remain finite. Its ecosystems would possess thresholds. The species might be biologically different from humans, yet the planetary constraints would be familiar. Energy use leaves waste. Mining moves matter. Population requires food. Agriculture changes land. Industry creates heat and chemical products. Any civilization must manage these consequences. Perhaps this is why the Silurian hypothesis feels like more than a curiosity. It asks whether civilizations leave a repeated pattern: rapid growth, resource extraction, atmospheric disturbance, ecological stress, then disappearance. If such cycles occurred before, the geological record might contain several narrow events resembling industrial pulses. No evidence currently supports this sequence. Ancient climate events have natural explanations, but the pattern remains useful as a warning about what our own layer could become. A civilization does not need a predecessor for the lesson to matter. Humanity can imagine its future from first principles. Suppose we vanished. Within days, electrical grids fail. Within years, buildings begin collapsing. Within centuries, forests cover many cities. Within thousands of years, coastlines change and sediment buries ruins. Within millions, most recognizable structures disappear. The atmospheric and chemical signals remain longer. The civilization becomes a boundary. Now imagine another intelligent species evolving tens of millions of years later. Perhaps it descends from an animal living today. Perhaps from a lineage that does not yet exist. It develops language, tools, science. It studies the rocks. Eventually, it reaches the layer created by humanity. What would it conclude? The researchers might first notice a sudden decline in biodiversity, then a spread of unusual species. They might find carbon-isotope changes, particles of altered polymers, concrete-like fragments, metal concentrations, radioactive anomalies. The evidence would suggest an event unlike ordinary volcanism or impact. Perhaps they would reconstruct an industrial species. They might never know our appearance at first. Bones would eventually reveal that a primate was involved. Anatomists could reconstruct the human body: hands with opposable thumbs, a large brain, upright walking, teeth shaped by an omnivorous diet. But anatomy would not reveal civilization fully. The future scientists might debate whether humans created the global signal or merely lived through it. They would search for associations: human remains beside tools, tools beside buildings, buildings beside chemical pollution. Gradually, the connection would strengthen. They might learn that humans controlled fire, built machines, and traveled across the planet. Could they recover our languages? probably only in fragments. Most writing would vanish. Stone inscriptions might survive in protected environments. Ceramic markings could remain. Certain metal plaques might endure. Objects left on the moon could provide clearer information. Perhaps they would discover one of our spacecraft. Its manufactured geometry would be unmistakable. Inside, damaged but recoverable patterns might encode images or data. For the first time, the future species could see human faces. They might hear reconstructed sound, a voice separated from its speaker by millions of years. To them, humanity would be the lost civilization. The idea reverses our position. We are accustomed to imagining ourselves as the archaeologists, but deep time makes everyone an artifact eventually. Our present world, filled with urgency and detail, will one day become an ancient mystery if another intelligence survives to study it. This perspective changes the meaning of preservation. Humanity cannot save every object. No archive is eternal, but deliberate records can increase the chance that future beings understand more than our pollution. We could leave durable scientific and cultural archives, not only on Earth, on the Moon, within stable underground environments, on spacecraft traveling beyond the solar system. We could encode languages, biology, history, music, mathematics, and warnings. Such archives would not guarantee remembrance. They might never be found. They might be damaged or misunderstood, but they would offer a fuller record than the chemical layer alone. Without them, the future may know us mainly through environmental disturbance. With them, perhaps it could know that we were more than our emissions, that we studied the universe, created stories, loved one another, asked questions about the past, worried about the future, tried, however imperfectly, to understand our place within deep time. There is humility in leaving such a message. It admits that civilization may not be permanent. Many cultures build monuments to declare power. A deep time archive would declare vulnerability. It would say that we knew Earth could erase us, that we understood the fragility of memory, that we hoped someone might one day find the evidence and recognize a mind behind it. Yet perhaps the most meaningful legacy is not an archive. It is survival. A civilization lasting millions of years would not need to introduce itself through one narrow layer of disruption. Its presence would become woven through planetary history. It might guide ecosystems, protect biodiversity, move asteroids away from dangerous paths, stabilize climate, restore damaged environments, spread carefully through the solar system. Its geological record would include not only a moment of pollution, but a long pattern of deliberate stewardship. Could such influence be distinguished from nature? Perhaps only partly. A successful civilization might become so integrated with its world that its actions resemble stable natural processes. Its legacy would be a planet remaining habitable. This is a quieter vision of intelligence, not domination, maintenance, not escaping nature, participating consciously within it. Human civilization often describes progress through what it can control: rivers redirected, mountains excavated, forests cleared, atoms split, genomes edited, planets reached. But the highest form of control may be restraint, the ability to act and choose not to recognize a threshold before crossing it, to leave resources unextracted, to preserve complexity that cannot be recreated, to understand that power over a system does not equal freedom from dependence upon it. Every civilization remains physical. It requires energy. It exists inside an environment. Even a society spreading through space depends upon stars, planets, materials, and stable laws of nature. There is no point at which intelligence becomes separate from the universe. Technology rearranges nature. It does not escape it. Perhaps civilizations disappear when they mistake rearrangement for independence. They begin to believe that ecosystems are replaceable, that atmosphere is an empty space for waste, that oceans are too large to change, that resources are unlimited, that technological solutions will always arrive before consequences. The planet eventually corrects these assumptions, not through intention, through physics. Crop yields respond to heat and water, coastlines respond to rising seas, species respond to habitat loss, infrastructure responds to storms, economies respond to resource limits. Civilization must either adapt or contract. This may be the universal challenge of technological life. The laws are different on every planet in detail. Gravity varies, atmospheres differ, oceans may be deeper, stars may be dimmer or more active, but limits remain. Any species capable of planetary influence must learn planetary feedback. It must recognize that the world responds. A civilization that understands this may survive. One that ignores it may leave a short, sharp signature. The great filter, if it lies ahead, may therefore be less like a sudden disaster and more like a failure to mature. Not one asteroid, not one war, not one machine, a long inability to align knowledge, cooperation, and power. The civilization knows enough to change the planet, but not enough to govern itself. It becomes trapped between capability and wisdom. Humanity stands somewhere within this transition. We possess remarkable knowledge. We can reconstruct the history of life from fossils, measure the composition of distant atmospheres, predict eclipses centuries in advance, detect particles smaller than atoms, send machines beyond the planets, sequence genomes, observe the universe as it existed billions of years ago. We are not ignorant of our influence. The question is whether understanding can become coordinated action. There are reasons for hope. Civilizations have solved large problems before. Diseases have been reduced or eliminated. Pollution has been controlled in many regions. Damaged ecosystems have recovered when protected. International agreements have addressed threats extending beyond borders. Technologies have become cleaner and more efficient. Knowledge spreads rapidly. Millions of people work to understand climate, energy, conservation, agriculture, and long-term risk. Humanity is capable of learning. It is also capable of empathy extending beyond immediate communities. People protect species they may never see, preserve forests for future generations, study dangers unlikely to occur within their lifetimes, build instruments whose results will be used by people not yet born. These actions reveal a capacity for deep time thinking. That capacity may be one of our greatest survival tools. The same mind that imagines a civilization before humanity can imagine humanity after the present crisis. We can see ourselves from the perspective of future geology. We can ask what layer we wish to leave, a narrow boundary of rapid damage followed by silence, or the beginning of a long-lived civilization that learned to remain. The rocks cannot answer for us. They record the answer after it is made. Suppose humanity succeeds. Fossil fuel use declines. The climate eventually stabilizes. Ecosystems are protected and restored. Waste becomes material for new production. Energy comes from sources compatible with a habitable planet. Technology supports resilience rather than constant extraction. The solar system is explored carefully. Knowledge is preserved in many places. Civilization continues for thousands, then millions of years. What would become of the Silurian question? Perhaps future humans would still search ancient rocks for earlier intelligence. Perhaps they would conclude with increasing confidence that no industrial civilization preceded us. But the question would remain valuable as the story of a danger avoided, a reminder of how easily our brief beginning could have become our entire history. A civilization surviving deep time might look back upon the 21st century as a narrow passage, the moment when the species first saw the whole planet, first measured its own influence, first acquired technologies capable of both destruction and preservation, first had to decide whether intelligence meant only greater power or greater responsibility. Perhaps every long-lived civilization remembers such an interval, a dangerous adolescence preserved in archives, a period when collapse was possible. The survivors may view it with disbelief, how close they came to becoming a thin layer, how nearly their songs, cities, and discoveries were reduced to carbon and plastic. If humanity fails, however, the planet will continue. This is important. Civilizational collapse is not the same as the end of Earth. Life has survived asteroid impacts, volcanic catastrophes, climate transitions, and mass extinctions. A severe human-caused disruption could cause immense suffering and biological loss while leaving some organisms alive. Forests could return in altered forms. Oceans would eventually reach new balances. Evolution would continue. Over millions of years, new species would appear. The biosphere would not restore every lost lineage. Extinction is permanent, but life as a whole may persist beyond us. Earth does not depend upon human civilization. Human civilization depends upon Earth. This asymmetry is easy to forget. We often speak of saving the planet. The planet has survived conditions far more extreme than humanity could tolerate. What is truly at risk is the stable world supporting modern societies and the web of species sharing it with us. Earth will continue orbiting the Sun. The question is what kind of life will accompany it. A future intelligent species could arise after us, perhaps from primates, birds, marine mammals, or a lineage impossible to predict. It might discover our chemical boundary. To that species, humans would appear almost mythic, an animal that changed the atmosphere, moved minerals between continents, placed objects on the moon, then vanished. Would they see us as a warning, a mystery, a predecessor? Would they wonder whether our civilization understood what was happening? The answer may survive in some archive, or it may remain unknowable. Perhaps they would debate two possibilities. One group might argue that humans were intelligent, but unable to cooperate. Another might suggest that the environmental disturbance was accidental and not understood until too late. A third might believe we left Earth and continued elsewhere. Without evidence, the story would remain incomplete. The future researchers might call our boundary by a name we would never recognize. They might not know the word humanity. They might reconstruct us from fossils and classify us among extinct mammals. Our machines would become technofossils. Our age would become a chapter in their textbooks. The civilization asking whether it was first would discover that it was not. The Silurian Hypothesis would become real for them. There is something profoundly strange about imagining our entire world from this distance. The conversations happening now, the traffic outside, the lights in windows, the satellites moving overhead, the music, markets, conflicts, and ordinary routines. All of it could become one thin line. A future hand might touch that line inside a cliff. The person would stand in daylight beneath constellations changed by the motion of stars. Our continents would no longer have their present shapes. Our cities would be gone. Yet the layer would say that something happened. A technological species lived here. For a brief time, Earth carried a global civilization. The line might be all that remains. But it has not been written completely. We are living inside it. The final pattern is still forming. Geology usually appears fixed because we study the past after events are finished. Our own layer is different. Its future depends upon decisions, the amount of carbon released, the number of species lost, the quantity of plastic produced, the degree of warming, the duration of industry, the possibility of recovery. These are not yet ancient facts. They are active processes. The Silurian Hypothesis may never reveal an earlier civilization, but it reveals something about this one. It shows that permanence is an illusion, that the planet records consequences more faithfully than intentions, that technological power can become visible across millions of years, and that a civilization may have only a short interval in which to learn how to use that power without becoming its own extinction layer. Perhaps the galaxy is silent because few civilizations learn. Perhaps it is silent because the survivors become quiet. Perhaps there is no great filter ahead at all. Humanity may be among the first technological species to appear in this region of the universe. There may be no ancient example to follow, and no warning from another world. In that case, our choices become even more significant. We would not merely be protecting one civilization. We could be protecting one of the earliest opportunities for the universe to become aware of itself. Through us, matter studies stars. Atoms arranged inside human brains reconstruct the beginning of the cosmos. The universe produces beings capable of asking how old it is, whether life exists elsewhere, whether civilizations came before. This awareness may be rare. It may also be fragile. A species does not need to believe it is cosmically important to recognize the value of preserving consciousness, knowledge, and life. Even if intelligence is common, every civilization contains experiences that will never appear in exactly the same form again. Every language represents a unique way of organizing thought. Every culture preserves a particular history. Every individual carries a world that disappears at death. Civilizational survival protects this accumulated complexity. The greatest loss in collapse would not be buildings. It would be possibility. Scientific discoveries never made, art never created, lives never lived, questions never asked, worlds never explored. The future is not empty time. It is potential experience. A civilization surviving for another million years could become almost unrecognizable. Human descendants might adapt to other planets, merge with technology, create new forms of culture, understand physical laws currently beyond us. They might discover life beneath the ice of another moon, detect an atmosphere shaped by distant intelligence, find an ancient probe drifting through the solar system, or finally uncover a true technosignature hidden inside Earth's oldest rocks. None of these possibilities exist if the civilization ends early. Survival is the doorway through which every distant future must pass. This gives the mystery a quiet urgency. We search for lost civilizations partly because we fear becoming one. The ruins we imagine beneath ancient sediment are reflections. They show us our cities without people, our machines without power, our knowledge without readers. They compress the modern world into chemistry. The image is haunting because it is physically possible, not inevitable. Possible. The difference between those words contains the space for action. Civilization may be fragile, but it is not helpless. It can observe its own trajectory. It can change energy systems, protect ecosystems, reduce dangers, preserve knowledge, build cooperation, plan across generations. No earlier species is known to have possessed this ability at a planetary scale. Humanity can model its own future before experiencing it. That may be our most important form of intelligence. Not the ability to build machines, the ability to imagine consequences. A civilization able to see its possible ruins has an opportunity to avoid them. Perhaps this is the true test. The great filter may not ask whether a species becomes intelligent. It may ask whether intelligence can look honestly at itself, whether it can accept limits, whether it can value a future it will not personally witness, whether it can transform fear into coordination rather than denial, whether it can become the first civilization on its world without becoming the last. Night settles across Earth. Cities shine along coasts and rivers. Aircraft move between points of light. Signals pass invisibly through the atmosphere. Beneath the ocean, new sediment settles over particles produced by our age. In lakes, pollen and metal enter thin layers of mud. Glaciers trap bubbles of modern air. On the moon, human footprints remain beneath a black sky. The geological signature is already forming. But the story does not need to end at the boundary. The layer can mark a beginning. A moment when a young technological species first became powerful enough to threaten its world and aware enough to choose another path. Perhaps future geology will show a disturbance followed by stabilization. A pulse of carbon, then recovery. A loss of species, then long protection. A period of waste, then careful cycles of material. The rocks might reveal that something changed twice. First the planet, then the civilization. Future beings may look at the boundary and recognize not only crisis, but learning. They may conclude that the species survived its first encounter with planetary power, that it saw the filter and passed through. For now, we cannot know whether the galaxy contains older civilizations. We cannot know whether some crossed the same threshold. Perhaps silent worlds around distant stars preserve the remains of those that failed. Perhaps quiet, enduring societies watch without revealing themselves. Perhaps Earth is the first place where this question has ever been asked. But we know one civilization exists. It is here. It is young, and its future has not yet become a fossil. The planet continues turning beneath the stars. Our lights remain visible. Our voices remain alive. The thin layer is still open, and within it humanity is deciding whether it will become a brief chemical mystery or a civilization capable of remembering itself. We began with a haunting possibility. Long before human beings appeared, perhaps another civilization rose upon Earth. Perhaps it crossed oceans that no longer exist. Perhaps it built settlements on continents since broken apart. Perhaps it learned to extract energy, transform materials, and study the sky. Then it disappeared. Its buildings collapsed. Its machines corroded. Its coastlines sank. The crust beneath its cities folded, melted, or descended into the mantle. Millions of years passed. And when humanity finally arrived, almost nothing recognizable remained. It is a powerful story, but science must separate a powerful story from a supported history. At present, Earth provides no confirmed evidence of a technological civilization before humanity. No manufactured object has been found inside reliably dated rock from the age of the dinosaurs. No ancient mine has been shown to predate tool-making species. No sedimentary boundary contains the complete combination of artificial compounds, refined metals, isotopic disturbances, and biological changes that would require an industrial explanation. The climate crises of deep time can be explained through volcanism, impacts, changes in oceans, and the activity of life itself. The fossils reveal remarkable animals, but not factories. The rocks reveal planetary transformations, but not forgotten nations. The simplest conclusion remains that humanity is the first known industrial civilization on Earth. That answer may feel less dramatic than the mystery, yet it is extraordinary in its own way. For more than 4 billion years, Earth existed without cities. Rain fell before there were roofs. Rivers crossed continents before there were bridges. The moon moved through the sky before any eye understood its orbit. Life began, changed the atmosphere, filled the oceans, spread across land, and survived repeated catastrophes. Countless creatures sensed their surroundings. Some remembered, some communicated, some used tools, some cared for their young and learned from one another. But as far as the evidence shows, none created a technological world until very recently. This makes civilization not an ordinary feature of the planet, but a new event in its history. A late experiment, a thin flame appearing near the end of an ancient night. The Silurian Hypothesis does not prove that another civilization came before us. Its deeper value is that it teaches us how difficult civilization would be to recognize after deep time. It asks us to imagine archaeology after buildings have become chemistry. It replaces the search for statues with the search for isotopes. It replaces buried highways with changes in sediment. It replaces names and languages with patterns of carbon, metal, plastic, and extinction. The hypothesis turns civilization into a planetary event. That shift in perspective is important. Human beings experience civilization from inside it. We see homes, roads, schools, markets, laboratories, museums, and screens. We understand these things through purpose. A road is a path between places. A library is a store of knowledge. A power station supplies energy. A spacecraft carries instruments beyond Earth. But geology does not preserve purpose easily. It preserves material. Concrete becomes a strange stone. Copper becomes an unusual concentration in sediment. A landfill becomes a compressed mixture of compounds. A city becomes a region of accelerated erosion and unfamiliar chemistry. A civilization's meaning disappears before its matter does. This is why a lost civilization could be recognized only imperfectly. Even if future geologists proved that industry existed during some ancient interval, they might never learn who created it. The builders may have possessed art, humor, rituals, science, and relationships as complex as ours. None of those experiences would appear clearly within an isotope ratio. A carbon disturbance might show that fuel was burned. It would not reveal the songs heard beside the fires. A concentration of metal might reveal manufacturing. It would not reveal whether the metal became a medical instrument, a musical object, a tool, or a weapon. A sudden spread of species might reveal agriculture and transport. It would not reveal the taste of food or the meaning of a shared meal. Deep time preserves consequences more easily than lives. That is perhaps the saddest truth in this journey. A civilization may contain billions of inner worlds. Every person remembers places that exist nowhere else in exactly the same way. Every language holds expressions that cannot be translated perfectly. Every generation inherits unfinished stories. Yet if the civilization disappears, geology compresses all of that richness into a small number of physical signals. A layer becomes the shadow of an age. The individuals are gone. Their names are gone. Their reasons are gone. Only the altered planet remains. This helps explain why apparent mysteries in ancient rock must be approached with care. Human imagination naturally restores the missing lives. A straight fracture becomes a wall. A mineral sphere becomes a manufactured object. An unexplained warming event becomes industrial collapse. We are drawn toward intentional explanations because intention is familiar to us. But nature is capable of patterns more complex than our intuition expects. Crystals create geometry. Erosion creates structures resembling ruins. Volcanoes change atmospheres. Microorganisms transform entire planets. Natural nuclear reactions can occur underground. Asteroid impacts distribute rare metals across the world. Earth does not need hidden engineers to create astonishing evidence. The standard for discovering an earlier civilization must therefore be high. Not because science is unwilling to accept a remarkable conclusion, because a remarkable conclusion deserves evidence strong enough to survive every reasonable doubt. The discovery would need to appear in independent samples. The dates would need to agree. Contamination would need to be excluded. Known geological and biological processes would need to fail as explanations. Several technosignatures would need to align within the same narrow interval, Only then would the idea move from speculation toward history. Perhaps such evidence will never be found. The silence of the rocks may continue. Future instruments will become more sensitive. Researchers may learn how plastics change after millions of years. They may identify new forms of molecular preservation. Cores may be taken from regions never sampled before. The moon may reveal fragments of ancient Earth blasted into space. Mars and Venus may teach us how planets preserve or erase their pasts. Old museum samples may produce discoveries when examined with new techniques. Yet every improvement may strengthen the same conclusion. There was no industrial world before ours. If that conclusion becomes increasingly secure, it does not make the search a failure. It gives humanity a clearer place within Earth's story. We may be the first species here to understand geological time, the first to recognize that continents move, the first to reconstruct vanished oceans from stone, the first to understand that extinction can be permanent, the first to know that a civilization can become a layer. This knowledge carries a quiet responsibility. Earlier life altered Earth without understanding what it was doing. Photosynthetic microbes released oxygen, transforming the atmosphere and changing which organisms could survive. Plants changed weathering, rivers, soils, and carbon storage. No organism planned these revolutions. Humanity is different because it can measure its effects while they are occurring. We can observe atmospheric gases from year to year. We can watch forests change through satellites. We can track glaciers, ocean temperatures, species populations, and chemical cycles. We can model possible futures. We can imagine our own cities abandoned. We can picture our civilization as an ancient mystery. Awareness does not guarantee that wise choices will follow, but it creates the possibility. The ability to see a consequence before it is complete may be one of the most important thresholds intelligence ever crosses. Perhaps this is what separates a temporary technological species from a lasting civilization. Not greater power, greater memory. A long-lived civilization must remember beyond one generation. It must preserve lessons after the people who learned them are gone. It must recognize dangers whose full effects arrive slowly. It must care about inhabitants of a future it will never personally see. In this sense, geology is more than the study of ancient rock. It is a form of communication across time. The planet shows us what happened when oceans warmed, what happened when carbon increased, what happened when impacts darkened the sky, what happened when ecosystems lost too many branches. The ancient world cannot speak, but its consequences remain. A fossil is a message without intention. A sedimentary boundary is a warning without an author. Humanity is capable of reading these messages. Whether we respond to them is part of the story still being written. Imagine again the future geologist. Millions of years have passed. The species is not human. Perhaps it is descended from birds, mammals, or a lineage that does not yet exist. Its body and senses are unfamiliar, but it understands chemistry and time. It enters a quarry where layers of ancient sediment rise along a wall. Most of the rock appears ordinary. Then one narrow boundary begins producing unusual measurements. Carbon isotopes shift. Tiny particles contain altered polymers. Metals appear in combinations unlike the layers above and below. Radioactive daughter products mark a brief interval. The bones of domesticated animals become abundant. Many wild species disappear. Sediment shows accelerated erosion. The future researchers collect more samples. The pattern appears in distant regions. It is global. It is brief. And it is difficult to explain through ordinary geology alone. Slowly they reconstruct us. They learn that one species moved material around the planet, that it used buried carbon for energy, that it produced artificial compounds, that it changed ecosystems and atmosphere. Perhaps they find human fossils and recognize the hands capable of precise manipulation. Perhaps they uncover a ceramic fragment bearing repeated marks. Perhaps a mission to the moon discovers equipment still resting near an ancient landing site. Inside a protected component, a pattern remains. Images, numbers, sound encoded in a damaged but readable form. For the first time, the researchers encounter not only our consequences, but our attempt to communicate. They see a human face. They hear wind moving through trees. They hear waves, birds, music, and a voice from a species absent for ages. The message may be incomplete. Its language may be difficult to recover, but its existence changes the layer. The chemical event becomes a civilization. The extinct primate becomes a people. Perhaps that future will never occur. humanity may survive and remain the interpreter of its own beginning. We may carry our history away from Earth, preserving it across planets and habitats. Our descendants may continue studying the first industrial layer without allowing it to become the final human layer. They may look back upon this age as an early dangerous transition, a time when civilization learned that planetary influence and planetary responsibility must grow together. If that happens, the Anthropocene will not be an epitaph, it will be a turning point. A narrow signal marking the moment a species first became aware of itself as a geological force. The following layers might tell a different story. Carbon gradually stabilizes, pollution declines, forests recover, species are protected, materials move through careful cycles, cities remain, but their chemistry becomes gentler. Technology becomes more advanced and less destructive. The civilization's signature continues, not as one violent pulse, but as a long pattern of maintenance. Perhaps that is what a mature techno-signature looks like. Not a planet covered in waste heat and smoke. A planet remaining habitable despite the presence of powerful intelligence. From a distant star, such a civilization might be difficult to recognize. Its atmosphere would appear balanced. Its ecosystems would remain active. Its energy use might release little obvious pollution. The most successful civilizations could be almost invisible because they have learned not to turn their worlds into alarms. Cosmic silence may therefore contain more than absence. It may contain restraint, or distance, or civilizations separated from us by time. It may contain ruins whose signals have faded. It may contain living worlds that never produced industry. And it may contain nothing technological at all within the region we can currently observe. We do not know. The uncertainty remains. But the Silurian question gives that uncertainty a new shape. When we look toward another planet, we should not ask only whether someone is living there now. We can ask whether someone lived there before. We can search for atmospheres recovering from ancient disturbance, surfaces containing strange distributions of material, orbital debris older than any active signal, machines resting on airless moons, spectra that reveal a brief chemical event in a world's distant past. The first evidence of alien civilization may be archaeological rather than conversational. We may discover not neighbors, but predecessors. A society whose light reached us after its cities went dark. A technological layer on a planet we can never visit. A probe moving through space after forgetting. If machines can forget the purpose given to it, such a discovery would be both comforting and lonely. It would prove that intelligence was not unique to Earth, but it would also reveal that intelligence can vanish. We would inherit no simple instructions. A dead civilization cannot tell us how to survive. Its ruins might warn us, but interpretation would remain ours. Perhaps its collapse had nothing to do with technology. Perhaps its star changed. Perhaps an impact arrived. Perhaps the civilization survived elsewhere. Archaeology rarely restores every cause. It offers fragments and asks the living to learn carefully. This is also true of the imagined civilization beneath Earth's rocks. If evidence were found tomorrow, the discovery would not instantly produce a complete history. There would be years of disagreement. Natural explanations would be tested. The age of the layer would be refined. Researchers would search other continents. The public imagination would fill with faces, cities, and dramatic endings that the evidence could not support. Science would need to remain patient. Perhaps all that could be said at first would be simple. During this interval, matter was arranged in a way that suggests technology. Something happened here. Someone may have been present. That small sentence would change humanity forever. We would no longer be the beginning of civilization on Earth. We would become its continuation. Our planet would have hosted more than one age of awareness. Human history would sit above another history, separated by a silence longer than our species has existed. The ground beneath every city would feel different, not because ruins necessarily lay below it, but because Earth itself would become an inherited world, a world that once belonged to other minds. Yet until evidence arrives, we should not confuse wonder with conclusion. The mystery is valuable without pretending it has been solved. A scientific question can be beautiful, even when the most likely answer is no. Did an industrial civilization exist before humanity? Probably not, according to everything currently known. Could deep time erase much of a short-lived civilization? Yes. Would some global chemical traces likely survive if that civilization were widespread and industrial? Also yes. Have those traces been found? No. These answers can exist together. They leave a small space for possibility surrounded by a much larger body of evidence. That is often where science lives. Not within perfect certainty, within carefully measured uncertainty. The purpose is not to close imagination. It is to give imagination a structure strong enough to carry truth. Tonight, beneath every sleeping city, layers of earlier worlds rest in darkness. Some formed beneath oceans, some beneath forests, some during warm eras when no polar ice existed. Others record ash, extinction, or the slow movement of ordinary life. The rocks contain shells from vanished seas, pollen from forests without human names, footprints made by animals under constellations different from ours. They contain no confirmed city, older than humanity. But they contain something equally profound. They contain a planet that has never stopped changing. Civilization lives upon the surface of that change. We build as though the ground is fixed. We draw borders as though continents remain still. We speak of permanent structures on a planet where mountains are temporary. Deep time does not make human life meaningless. It makes every living moment rare. A city is precious not because it will remain forever, but because it exists now as a meeting of minds. A language matters not because stone will preserve every word, but because people can understand one another while the language is alive. Knowledge matters because it can cross generations, even if it cannot cross eternity. Civilization is not valuable only when it becomes permanent. Nothing physical may be permanent. Its value lies in what it allows life to experience and understand before the world changes again. Perhaps humanity is the first civilization on Earth. Perhaps it will be the only one. Perhaps another intelligence will emerge long after us and reconstruct only fragments. Perhaps human descendants will still be here, carrying memory into an age when today's oceans and continents are gone. Every possibility begins within the same present moment. The layer has not closed. The machines still operate. The libraries still contain their words. The voices have not become silence. We are not yet a technofossil. We are the living civilization deciding what its fossil will mean. The deepest lesson of the Silurian Hypothesis may therefore have little to do with imaginary beings from the past. It may be a lesson about attention. Look closely at the planet. Understand the systems that preserve life. Recognize how quickly power becomes consequence. Preserve knowledge beyond short political and personal horizons. Build archives, but also build a world in which someone remains to read them. Search for earlier intelligence, but do not become so fascinated by vanished civilizations that we neglect the ones still alive. The earth beneath us is ancient. The civilization upon it is young. Between those two facts rests both mystery and responsibility. We may never uncover a hidden predecessor. We may never find an artificial layer beneath the dinosaurs. But by asking whether Earth erased another civilization, we learn how Earth might one day erase ours. And by understanding that possibility, we gain a chance to choose a different ending. Outside, the planet continues its quiet motion. The continents drift too slowly to be felt. Rivers carry grains toward the sea. Dust settles through the atmosphere. New sediment forms beneath dark water. The moon keeps the footprints already placed upon it. Starlight crosses distances older than every human memory. For tonight, no ancient machine rises from the ground. No forgotten voice speaks from the rocks. There is only the evidence we have, the possibilities we can imagine, and the living world still present around us. Perhaps we are not standing above the ruins of an earlier civilization. Perhaps we are standing at the beginning of the first. And perhaps the question that matters most is no longer whether someone came before. It is whether anyone will come after and find that we learned to remain. Until then, Earth keeps turning, the layers continue forming, and beneath the silence of deep time, our unfinished story is still being written.